through space at 470,000 mph, and you feel nothing. We are about to journey from your backyard to the edge of everything we can ever know. You will see stars that rain metal, voids where galaxies vanish, and structures so massive they should not exist. If you are ready to feel impossibly small and absolutely amazed, like and subscribe. Prepare yourselves. We begin. Light moves faster than anything in our universe. Close your eyes and open them again. In that single blink, light traveled 186,000 mph. That distance wraps around Earth more than 7 times. Your brain cannot process this speed because nothing in your daily life moves anywhere close to it. Every photon leaving a bulb in your room crosses the entire space in billionths of a second. The light hitting your face right now left its source so recently that the moment feels instant. But stretch that single second across space and the numbers become staggering. While you count to 1, light races from Earth past the moon with distance to spare. Picture a racetrack circling the planet at the equator. Light completes that loop 7 and 1 or 2 times before your heart beats once. The fastest jet ever built would need over 3 weeks to match what light does while you blink. Our fastest spacecraft, Voyager 1, crawls at 38,000 mph. Light mocks that speed. It covers the same distance Voyager travels in 1 hour in less than 1 second. This speed sets the scale for everything beyond Earth. When you look at the moon, you see it as it was 1.4 seconds ago. The light left its surface, crossed the void, and entered your eye after a short delay. You never see the present moment of anything in space. You always see the past. Scientists measure cosmic distances using this speed. 1 light second equals 186,000 mph. 1 light minute multiplies that by 60. 1 light year explodes the number beyond easy comprehension. That single year of light travel covers almost 6 trillion miles. Everything you will discover next depends on understanding this foundation. Light sets the cosmic speed limit. Nothing with mass can ever reach it, let alone surpass it. This limit creates barriers in space that technology cannot break. The universe spreads so far that even light racing at maximum speed forever cannot show us everything that exists. Think about watching a lightning storm from miles away. You see the flash, then wait for thunder. Light reaches you instantly, but sound lags behind. In space, even light lags. When you observe distant objects, you witness ancient history. The farther you look, the older the view becomes. This single second of light travel contains more distance than most people cross in their entire lives. Your car moving at highway speed for 1 full year covers around 600,000 mph. Light does that in 3 seconds. The gap between human experience and cosmic scale begins right here with this single measurement. We built our first understanding of space by timing light. Scientists bounced laser beams off reflectors. Astronauts placed on the moon. They measured how long light took to make the round trip. The answer revealed the exact distance, 238,000 mph. Later, they used the same method to map distances to planets, asteroids, and eventually stars. But here is what makes this speed both beautiful and limiting. Light connects everything we can observe. Without it, we see nothing. It carries information from distant galaxies, dying stars, and ancient cosmic events. Yet its finite speed also traps us. We can only know about places where light has had time to reach us since the universe began. In 1 second, light accomplishes what seems impossible by human standards. It outruns every storm, every rocket, every natural force we know. That single second becomes the measuring stick for the cosmos. But compared to what comes next, even this incredible speed starts to feel agonizingly slow. Stand in your backyard and look up at the moon. That glowing disk appears close enough to touch. Your mind tricks you into thinking the distance might be manageable. The truth crushes that illusion immediately. 238,000 separate you from the lunar surface. Every human who ever lived, walking in a single file line, would barely cover that gap. Take every step humanity has traveled since we first walked upright. Add every migration, every expedition, every journey across continents and oceans. Stack those distances end to end. The moon still sits beyond that combined total. Think about the longest road trip you ever took. Multiply it by thousands. The number still falls short. A commercial jet flying non-stop would need 20 days to reach the moon. Your car driving at highway speed without pause would take 6 months. Walking would consume decades. Only 24 humans ever traveled to the moon. 12 actually stepped on its surface. The journey took 3 days aboard the most powerful rockets ever built. Those astronauts crossed a void so vast that Earth shrank to a blue marble behind them. They looked back and saw their entire world, all 7 continents, every ocean reduced to something that fit behind a thumb. The Apollo missions consumed more fuel than thousands of cars use in their entire lifetimes. The rockets stood as tall as skyscrapers. All that engineering, all that power, all that risk, just to cross what appears as a short hop in the night sky. Between Earth and the moon sits almost pure vacuum. No air, no resistance, no matter except the occasional dust particle or stray atom. The emptiness stretches so far that you could fit every planet in our system side by side inside that gap. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, lined up together with room left over. This distance created problems the Apollo engineers never anticipated. Communication signals traveling at light speed took over 2 seconds round trip. Ask a question to mission control. Wait 1 second for your words to arrive. Wait another for the response. That lag became dangerous during emergencies. Decisions had to happen faster than light could carry advice. Temperature swings between Earth and Moon range from boiling to freezing. Radiation floods the space between, unfiltered by any atmosphere. Micrometeoroids whipped through the darkness at speeds that turned dust into bullets. The journey required spacecraft built like tanks, yet light enough to escape Earth's gravity. Modern technology makes the trip no easier. We abandoned moon missions not because they became simple, but because they remained brutally expensive. Each launch costs billions. The distance demands perfection. One failed component, one calculation error, one unexpected problem transforms a 3-day journey into a death sentence. The moon itself holds no air to breathe, no water to drink, no food to harvest. Astronauts carried everything they needed for the entire trip. The lander that touched the surface weighed less than a loaded truck, yet it held life support, fuel, computers, communications, and 2 humans. Engineering pushed to its absolute limits made those missions possible. Looking up tonight, the moon appears gentle and romantic. Poets write about its beauty. Lovers admire its glow. But the reality beats back any notion of easy travel. That distance separates the possible from the comfortable. We reached it through determination, not convenience. Television makes space travel look routine. Movies show characters hopping to the moon as easily as flying to another country. The real numbers tell a different story. That gap remains so wide that fewer humans have stood on the moon than have summited Mount Everest. The mountain at least stays attached to Earth. The moon sits at our doorstep compared to everything else in space. It represents the absolute closest target beyond Earth. Yet reaching it consumed the wealth and genius of a superpower at its peak. What comes next makes this distance look like a short walk down the street. Our star floods Earth with light every second of every day. You feel its warmth on your skin. You see by its glow. The energy arrives so reliably that you assume it travels instantly. That assumption hides one of space's most humbling truths. Light leaving our star takes 8 minutes and 20 seconds to reach your eyes. Right now you see that massive nuclear furnace as it looked before you finished breakfast. A lightning bolt traveling at light speed, racing across the void between that star and Earth, would need that same 8 minutes to complete the journey. The distance spans 93 million miles. Saying the number out loud does nothing to capture the scale. Your mind lacks any reference point for distances that vast. So imagine this instead. 100 Earths lined up edge to edge would barely cover that gap. The emptiness between us and our star swallows planets whole. Every photon warming your face began its journey 8 minutes ago in the star's core. It fought through layers of nuclear fusion, battled through crushing pressure, and finally escaped into space. Then it crossed the void at maximum speed. By the time it touches your skin, that photon has traveled farther than anything you will ever move in your entire lifetime. This delay creates a strange reality. If our star vanished right now, snuffed out like a candle, you would not know for 8 minutes. Earth would continue its orbit, bathed in light and heat, completely unaware of the disaster. Birds would sing, people would go about their day. Then, without warning, darkness would slam down like a curtain. Scientists use this distance as another measuring tool. They call it 1 astronomical unit. Everything beyond our star gets compared to this baseline. Mars sits 1.5 astronomical units away. Jupiter sprawls 5 times farther than Earth from our star. The outer planets push that number even higher. Light speed creates these unavoidable gaps. When you watch our star set over the horizon, you see it where it was 8 minutes ago, not where it sits now. That ball of nuclear fire has already moved millions of miles along its path through the galaxy. You observe its ghost position, frozen in time by light's travel delay. This 8-minute gap means we can never react to solar events in real time. When our star erupts with massive flares, the radiation burst travels toward Earth at light speed. We detect it 8 minutes after the eruption begins. By then, the high-energy particles are already crossing the void. Satellites, power grids, and communication systems have 8 minutes of warning before the storm hits. Sometimes that warning is enough, sometimes it is not. Think about all the other stars you see at night. Their light travels for years, centuries, even millennia before reaching your eyes. Our star, sitting practically next door, still requires 8 minutes. That relatively short delay hints at the vast loneliness of space. Even our closest stellar neighbor hides behind an 8-minute wall that light speed cannot shorten. The number affects how we explore space, too. Commands sent to spacecraft near our star take 8 minutes to arrive. The reply takes another 8 minutes to return. That 16-minute round trip makes real-time control impossible. Engineers must program spacecraft to think for themselves, to solve problems without waiting for instructions from Earth. Our star provides all the energy Earth needs to maintain life. Plants capture its light. Weather patterns follow its heat. Ocean currents respond to its radiation. All of that life-giving power travels across 93 million mm of absolute emptiness. The void between us and our star protects Earth from getting incinerated while still allowing enough warmth to keep water liquid. Ancient peoples assumed the sky was close. They imagined touching the stars, reaching the heavens with tall towers. Then measurements revealed the truth. Our star alone sits so far away that light, the fastest thing in existence, needs 8 full minutes to cross the gap. That realization marks the beginning of understanding just how isolated we truly are. But this distance to our star is nothing. What waits beyond makes 8 minutes feel like a blink. Mars glows red in the night sky, tantalizing us with possibility. It represents humanity's next target for exploration, maybe even colonization. Every few years, Mars swings close enough that the journey becomes theoretically possible. Even at closest approach, the planet remains so far away that most living things would die trying to reach it. 34 million miles separate Earth from Mars at the nearest point. That closest approach happens only when both planets align perfectly in their orbits. Miss that window and the distance balloons to over 250 million miles. The gap between shortest and longest routes dwarfs the distance to our moon hundreds of times over. A spacecraft traveling to Mars needs at least 6 to 29 months to complete the journey. No current engine can shorten that timeline significantly. Astronauts would float in a metal can, bombarded by radiation, watching Earth shrink behind them. Every supply must be packed before launch. Every drop of water, every meal, every breath of air, calculated down to the last ounce. The vacuum between Earth and Mars offers nothing. No rest stops, no rescue missions, no turning back once you commit to the trajectory. If something breaks, the crew must fix it with whatever tools and parts they brought. If they run out of food, they starve. If life support fails, they suffocate. The planet grows closer, but slowly, agonizingly, across millions of miles of dead space. Radiation exposure during the flight would exceed safe levels. Without Earth's protective magnetic field, cosmic rays and solar particles tear through spacecraft walls. Prolonged exposure damages DNA, increases cancer risk, and degrades organs. We have no perfect solution yet. Every proposal adds weight, and weight requires more fuel, and more fuel costs billions. Even at closest approach, signals from Mars take between 3 and 22 minutes to reach Earth, depending on exact positions. That communication lag prevents real-time assistance. Ask for help, and you might wait 44 minutes for an answer. In an emergency, you solve the problem alone, or you die waiting for advice that arrives too late. Mars itself offers a hostile environment. The atmosphere contains mostly carbon dioxide at less than 1% of Earth's pressure. Walking on the surface without a spacesuit would kill you in seconds. Temperatures plunge to 200 degrees below zero at night. Dust storms engulf the entire planet for months, blocking visibility and coating everything in fine toxic particles. Water exists on Mars, but locked in ice or hidden underground. Liquid water cannot survive on the surface because the air pressure is too low. It either freezes or evaporates instantly. Growing food requires ship soil or manufactured nutrients. Building shelter demands materials shipped from Earth or processed from Martian rock. Every basic need becomes an engineering challenge. The return journey requires fuel stored on Mars or manufactured there from local resources. No gas stations exist between planets. If the return fuel is lost, contaminated, or insufficient, the crew stays on Mars forever. That risk haunts every mission plan. The distance back to Earth equals the distance traveled to arrive. The exposure, the isolation, the danger doubles for anyone attempting a round trip. Compare this to historical exploration on Earth. Sailors crossing oceans could catch fish, collect rainwater, and breathe freely. If a ship sank, swimmers might reach shore. Mars offers none of these mercies. You drift through vacuum, entirely dependent on technology that must function perfectly for months without resupply or repair. Only machines have successfully landed on Mars so far. Rovers explore the surface, sending back photos and data. They represent our eyes on another world. But these robots are not alive. They do not need food, water, or air. They feel no fear. They do not care about radiation or loneliness. Sending humans requires solving problems that robots ignore. 34 million miles at closest approach still translates to an impossible barrier for most life forms. Bacteria might survive the journey in hibernation. Tardigrades could endure the radiation, but complex organisms like us, like dogs, like plants, require constant care across that void. Mars orbits farther from our star than Earth. The journey there crosses empty space, but that emptiness contains more than just vacuum. Between Mars and Jupiter stretches something unexpected. Movies show asteroid belts as dense fields of tumbling rocks. Spaceships weave through them, dodging collisions at every turn. Pilots sweat as boulders spin past their windows. This image plants itself firmly in popular imagination. The reality reveals something far stranger and more unsettling. The asteroid belt does exist between Mars and Jupiter. Millions of rocky fragments orbit our star in that region. Some measure only a few feet across. Others stretch for hundreds of miles, but the space between these rocks is vast, beyond comprehension. You could fly through the asteroid belt, blindfolded, and likely never pass close to a single one. The belt spans roughly 200 million miles across. Think about that width. It extends farther than Earth's entire orbit. Millions of asteroids scattered across this region sound crowded until you calculate the actual density. The average distance between asteroids measures around 600,000 km. That gap exceeds twice the distance from Earth to the Moon. If you stood on one asteroid, you might see the next one as a dim point of light. Maybe, probably not. The darkness and distance would hide most nearby rocks from view. You would float on your asteroid alone, surrounded by emptiness in every direction. The closest neighbor might sit so far away that traveling there would take months. Scientists estimated the total mass of the asteroid belt at roughly 4% of our moon's mass. All those millions of rocks combined weigh less than one small moon. Spread that tiny mass across 200 million miles of space, and the belt becomes incredibly sparse. Empty space dominates. Rock is the exception. Spacecraft crossing the asteroid belt require no special maneuvering. They fly straight through on predetermined paths. Mission control does not scramble to avoid collisions. The odds of randomly hitting an asteroid approach zero. Only when missions specifically target an asteroid for study do engineers plot careful intercept courses. Finding these rocks in all that space requires precision, not luck. This emptiness makes the asteroid belt less a barrier and more a distributed cloud of debris. Our star's gravity keeps the rocks orbiting in roughly the same plane. Jupiter's massive pull prevents them from clumping together into a planet. The rocks drift along their individual paths, separated by continental distances. Some asteroids follow elongated orbits that bring them close to Earth. These near-Earth asteroids occasionally make headlines when their paths intersect our planet's orbit. Even then, space is so vast that most pass millions of miles away. Direct impacts remain rare. The universe provides plenty of room for everything to miss everything else. Early astronomers discovered the first asteroids in the early 1800s. They expected to find a planet between Mars and Jupiter. Instead, they found Ceres, the largest object in the belt. It spans roughly 580 miles across. That makes it bigger than many countries. Yet, it represents only 1/3 of the belt's total mass. Every other asteroid combined barely equals Ceres twice over. The gaps between asteroids mean that mining them poses unique challenges. Companies dream of extracting valuable metals from these rocks, but each target orbits independently. Traveling from one asteroid to another consumes fuel and time. The space between them demands the same respect as interplanetary distances. These are not resources sitting next to each other on a shelf. They drift alone, separated by voids. This sparse reality teaches us something important about space. Even in regions we call crowded, emptiness rules. The asteroid belt contains millions of objects and remains almost entirely vacant. Density in space operates on scales that human intuition cannot grasp. What looks full is mostly void. The belt also demonstrates how much room exists in our system. Planets orbit in relatively flat plane, but the distances between them dwarf their sizes. Gravitational influence reaches far, but solid matter occupies almost nothing. We imagine space as filled with objects. The truth shows us ocean-like emptiness, with islands scattered impossibly far apart. Farther out, beyond the asteroid belt, something far more intriguing waits in Jupiter's orbit. Europa sits there, hiding an ocean that makes Earth's water supply look small. Jupiter's moon, Europa, looks like a cracked marble from a distance. White ice covers its entire surface, etched with dark lines that crisscross like scars. For decades, scientists considered it beautiful but dead. Then measurements revealed something impossible hiding beneath that frozen shell. Europa contains more liquid water than all of Earth's oceans combined. The entire volume of every sea, every lake, every river on our planet fits inside Europa with room to spare. That water sits locked beneath a layer of ice that might reach 10 to 15 millimeters thick. Under that protective shell, an ocean deeper than Earth's deepest trenches stays liquid, despite temperatures that should freeze it solid. Jupiter's gravity creates this miracle. The giant planet pulls on Europa with such force that the moon flexes and bends like rubber. This constant squeezing generates heat through friction. The ice layer acts as insulation, trapping that heat inside. The result is a subsurface ocean that might reach 60 miles deep in places. That depth swallows Mount Everest twice over. Evidence for this hidden ocean comes from magnetic field measurements. Europa generates a weak magnetic field that wobbles. That wobble indicates something conductive moving beneath the surface. Ice alone cannot produce this signal. Salt water can. The data points toward a global ocean containing more salt than Earth's seas, possibly harboring complex chemistry. The ice shell above this ocean constantly shifts and cracks. Long fractures called linear cover Europa's surface. Some of these features stretch for hundreds of miles. Dark material from below seeps up through these cracks, staining the ice. That contamination suggests the surface connects to the ocean beneath. Water might occasionally breach the ice, erupting in towering geysers before freezing and falling back down. Life might exist in Europa's ocean. Earth's deep sea vents support entire ecosystems without reliance on the star above. Bacteria and strange creatures thrive on chemical energy released by volcanic activity. Europa could host similar vents on its ocean floor. The combination of liquid water, chemical energy, and protection from radiation creates conditions where life might emerge. No direct confirmation exists yet. We have not drilled through Europa's ice. We have not sampled the water below, but the possibility drives mission planning. Multiple space agencies designed landers and submarines meant to pierce that shell. The technology required to bore through miles of ice in low gravity while operating remotely from Earth challenges engineering limits. Yet the prize might be worth any cost. Compare Europa's ocean to Earth's water supply. Our planet seems covered in water, but most of it spreads thin across the surface. Evaporation, weather, and solar radiation constantly cycle that water. Europa's ocean sits protected, stable, unchanged for potentially billions of years. That stability might allow chemistry to develop in ways Earth's dynamic surface prevents. The moon orbits Jupiter every 3 and 1/2 days. Each orbit takes Europa through intense radiation belts surrounding the giant planet. The surface receives doses that would sterilize any exposed life, but deep below, the ocean stays shielded. Radiation cannot penetrate miles of ice. Whatever exists down there lives in darkness, protected from the deadly environment above. Europa measures only slightly smaller than Earth's moon. Its small size tricks us into underestimating its significance. But volume matters more than surface area. That hidden ocean dwarfs any single body of water on Earth. The Amazon River, the Mediterranean Sea, Lake Ball, all of them together represent a fraction of what Europa contains. Temperature at the ocean floor might approach conditions found in Earth's deep sea. Chemical reactions between water and rock could release nutrients. Thermal vents could pump heat into the surrounding water. The ingredients for life mixed together in darkness. Billions of years passing while we stood on Earth looking up, unaware of what Jupiter's moon concealed. Other moons in our system might also harbor subsurface oceans. Enceladus, Titan, and Ganymede all show signs of liquid water beneath ice. But Europa remains the most studied, the most promising, the most likely to reveal whether life emerges wherever conditions allow. Farther out from Jupiter, Saturn commands attention with its own mysteries. Those famous rings inspire awe in every photograph, but those rings will not last forever. Saturn's rings stretch across 280,000 miles of space, creating one of the most recognizable sights in our system. Those gleaming bands of ice and rock have adorned the planet for as long as humans looked up. Every image from telescopes and spacecraft showcases their beauty. but those rings are dying before our eyes. Recent measurements reveal that Saturn loses its rings at an alarming rate. Every second, thousands of pounds of ring material rain down onto the planet's surface. Gravity pulls ice particles inward. They spiral down through the atmosphere and vaporize, lost forever. At this rate, the rings will vanish completely in less than 100 million years. 100 million years sounds distant, but in cosmic terms, that timeline is a blink. Dinosaurs walked Earth longer than Saturn will keep its rings. The rings you see tonight might look significantly thinner to your descendants in just a few generations. We live in a brief window where Saturn displays this magnificent feature. Scientists debate how the rings formed in the first place. One theory suggests a moon wandered too close to Saturn millions of years ago. Tidal forces ripped it apart, scattering debris into orbit. Another theory proposes that collisions between moons created the material. Either way, the rings are young compared to the planet itself. They might be only 10 to 100 million years old, making them recent additions to Saturn's appearance. The rings consist primarily of water ice mixed with rocky particles. Some chunks measure the size of dust grains. Others span several yards across. All of them orbit Saturn in a flat plane, held in place by gravity and the planet's rotation. The rings appear solid from a distance, but spacecraft flying through them would encounter mostly empty space with occasional ice pieces. 7 major ring sections exist, each labeled with letters. The A ring, B ring, and C ring are the most visible. Gaps between rings create dark bands where shepherd moons have cleared out material. These moons orbit within or near the rings, using their gravity to sculpt edges and maintain gaps. Without these shepherd moons, the rings would spread and blur over time. The rings shine bright because ice reflects starlight. Saturn itself appears dim and yellowish, but its rings dazzle with reflected brilliance. That brightness makes the rings visible from Earth through amateur telescopes. For centuries, observers admired Saturn's handles, as early astronomers called them. Only later did better optics reveal the true nature of these structures. Saturn's magnetic field drags charged particles from the rings. These particles follow magnetic field lines down into the planet's atmosphere. The process creates a ring rain that steadily drains mass. Spacecraft have detected this rain directly. They measured the flow rate and calculated how long the rings could survive. The answer shocked researchers. The rings are temporary, fading faster than anyone expected. Think about what this means. Every civilization that looks up at Saturn from now until the rings vanish will see them slightly different. Your grandchildren might see noticeably thinner bands. Their grandchildren might need powerful telescopes to detect remnants. Eventually, future astronomers will study Saturn with no rings at all, wondering if ancient records about their existence are accurate. This disappearance raises questions about other ring systems. Jupiter has faint rings. Uranus and Neptune sport thin, dark rings. None of them compare to Saturn's spectacular display. If rings are temporary, perhaps Saturn's current magnificence is rare, even in planetary terms. We live during a golden age where this planet shows off. The rings span from $4,000 above Saturn's clouds to over $80,000 out. That thickness provides volume, but the rings themselves are incredibly thin. In many places, they measure only about 30 ft from top to bottom. Imagine a disk of ice 280,000 nauters wide and thinner than a 10-story building. That fragility contributes to their impermanence. Gravity constantly wars with the forces holding rings together. Over time, gravity wins. Particles drift inward. Collisions scatter material. Magnetic fields drain charged particles. The system slowly unravels. Saturn cannot hold these rings forever. The planet's gravity ensures their destruction. Future generations might envy us. We see Saturn at its most beautiful, crowned with rings that catch starlight and inspire wonder. That crown slips away, falling into the planet piece by piece. Beyond Saturn, past the orbits of Uranus and Neptune, the Kuiper Belt extends the system farther than most people imagine. Beyond Neptune, where starlight dims and temperatures plunge to near absolute zero, a vast region of frozen objects circles our star. The Kuiper Belt stretches across billions of miles, extending roughly 30 times farther from our star than Earth orbits. That distance places it so far out that our star appears as just a bright point of light, no larger than any other star in the sky. This belt contains millions of icy bodies left over from when our system formed. They orbit in the cold darkness, never warming enough to melt. These objects range from small rocks to dwarf planets measuring hundreds of miles across. Pluto resides here, demoted from planetary status, but still dominating its neighborhood through sheer size. The Kuiper Belt begins around 30 times Earth's distance from our star and extends outward to 50 times that distance. That width spans billions of miles of space, making the asteroid belt look small by comparison. The sheer volume of this region dwarfs anything closer to our star. Yet it remains incredibly sparse. Like the asteroid belt, distance between objects measures in millions of miles. These frozen bodies consist mostly of ice, frozen methane, frozen ammonia, and rock. They represent the building blocks of planets, materials that never clump together into something larger. When the giant planets formed closer to our star, their gravity scattered debris outward. That debris settled into the Kuiper Belt, where it has orbited ever since. Some Kuiper Belt objects follow elliptical paths that bring them closer to our star periodically. When they approach, solar radiation heats their surfaces. Ice sublimates directly into gas, creating tails that we see as comets. Every comet you have ever seen originated from either the Kuiper Belt or the Oort cloud farther out. These visitors from the outer system provide glimpses of what exists in the deep freeze beyond the planets. Discovering the Kuiper Belt required patience and powerful telescopes. The region is so far away, and its objects reflect so little light, that detecting them challenges even modern instruments. Astronomers predicted its existence based on mathematical models, then spent decades searching. The first confirmed Kuiper Belt object beyond Pluto was found in 1992. Since then, thousands more have been cataloged. Temperature in the Kuiper Belt hovers around 370 degrees. At those temperatures, almost everything freezes solid. Chemistry slows to a near halt. Time moves differently here. Objects remain unchanged for billions of years. The frozen bodies we see today look almost identical to how they appeared when our system was young. Our star's light takes over 4 hours to reach the inner edge of the Kuiper Belt. That means any object there sees our star as it was 4 hours ago. The farther out you go, the longer the light delay. Communication with spacecraft exploring this region requires advanced planning. Send a command, wait hours for it to arrive, then wait hours more for confirmation. Only one spacecraft has visited the Kuiper Belt so far. New Horizons flew past Pluto in 2015, then continued onward to encounter Arrokoth, a smaller object deeper in the belt. The images sent back revealed surfaces untouched by weather or geology. Craters remained pristine. No atmosphere existed to erode features. These objects preserved their original state like fossils frozen in time. The Kuiper Belt marks the edge of what most people consider our system. Beyond it, density drops even further. Objects become scarce. Gravity from our star weakens to the point where other forces compete for influence. Yet the belt does not represent the true boundary. The system extends much farther still. Think about standing at the inner edge of the Kuiper Belt. You would see planets as distant points of light, requiring telescopes to resolve. Our star would shine bright but small, offering almost no warmth. The sky would be black, filled with more stars than you could count. You would feel utterly isolated, aware that Earth sits impossibly far behind you. The belt contains enough material to build dozens of Earth-sized planets. But that material never gathered together. It drifts in loose formation, orbiting our star at glacial speeds. Objects in the Kuiper belt take 200 to 300 years to complete one orbit. Entire human lifetimes pass while these frozen worlds make tiny progress around their paths. Scientists estimate the Kuiper belt might contain 100,000 objects larger than 60 nmi across. Millions more smaller objects fill the space between. But remember, this is space. Those millions of objects spread across billions of miles. Emptiness still dominates. What waits beyond makes even the Kuiper belt seem close. In 1977, humanity launched Voyager 1 toward the outer planets. The spacecraft carried a golden record containing sounds and images from Earth, intended for any civilization that might find it. Engineers designed Voyager to last 5 years. It has operated for over 40 years and continues sending data from farther away than any human-made object has ever traveled. Voyager 1 has crossed 14 billion miles. That number staggers the mind. The spacecraft has traveled so far that signals from it take over 21 hours to reach Earth. When Mission Control sends a command, they wait nearly 2 days for confirmation that Voyager received it. Every communication becomes an exercise in patience. Despite this incredible distance, Voyager 1 has barely left our system. It crossed the helop in 2012, entering interstellar space. The helipause marks where solar wind pressure drops below the pressure of interstellar particles. But crossing this boundary does not mean leaving our star's influence. Gravity reaches much farther than wind. Our star's gravitational influence extends thousands of times farther than Voyager has traveled. The Oort cloud, a spherical shell of icy objects surrounding our entire system, reaches perhaps 100,000 times Earth's distance from our star. Voyager would need 30,000 years at its current speed to reach the Oort cloud's inner edge. Escaping completely might take 300,000 years. Think about what this means. We launched our fastest spacecraft during the lifetime of people still alive today. That spacecraft has raced through space for over 4 decades without stopping. It has passed every planet, left all the familiar objects of our system behind, and crossed into the space between stars. Yet, it remains trapped in our star's gravitational well with millennia still ahead before it truly breaks free. Voyager moves at roughly 38,000 km/h. Nothing slows it down. No air resistance exists in space. It coasts on momentum gained from Earth's rotation, its launch rocket, and gravity assists from Jupiter and Saturn. That speed seems incredible until you compare it to the distances involved. At this rate, Voyager would need over 70,000 years to reach the nearest star system. The spacecraft carries power from a plutonium battery that converts radioactive decay into electricity. That battery degrades slowly, reducing available power every year. Mission Control has systematically shut down non-essential systems to conserve energy. The heaters went off first. Then scientific instruments one by one fell silent. Eventually, perhaps by 2025, Voyager will lack enough power to transmit data. It will continue traveling, but we will no longer hear from it. Even after it goes silent, Voyager will drift through space for millions of years. The golden record will remain intact, protected by its case. If another civilization ever encounters it, they will find a snapshot of Earth from the 1970s. Images of people, landscapes, animals, sounds of music, laughter, greetings in dozens of languages. A message from a species that threw a bottle into the cosmic ocean. Voyager 1 has outlasted the engineers who built it. Some have retired, others passed away. New generations manage the mission now, communicating with a probe designed by people who use slide rules instead of computers. The technology aboard Voyager is ancient by modern standards, yet it continues functioning in conditions more hostile than any test chamber could simulate. Radiation, cosmic rays, micrometeoroids, temperature extremes. None of these hazards stopped Voyager. The spacecraft survived because engineers overbuilt it. They added redundancy, shielding, and quality components. They tested everything multiple times. That extra effort decades ago keeps Voyager alive today. The spacecraft carries no fuel for propulsion. It cannot change course or speed up. Its trajectory was set during its gravity assists past the giant planets. Where it goes now depends entirely on how precisely those flybys were executed. So far, the calculations remain accurate. Voyager follows its planned path into the unknown. Humanity poured resources into sending Voyager to the outer system. We succeeded brilliantly. The mission returned more data than anyone hoped. It showed us Jupiter's storms, Saturn's rings, and views of planets we had only imagined. But the distance it covered, as impressive as it is, represents a tiny fraction of what separates us from other stars. Our doorstep extends farther than we thought possible. The Oort cloud waits out there, a vast sphere of frozen objects that marks the true edge of our star's domain. Far beyond the Kuiper Belt, beyond anything we have explored or photographed, a spherical shell of icy objects surrounds our entire system. The Oort cloud exists as a theoretical region predicted by mathematics, but never directly observed. Its existence explains where long-period comets originate. Its size defies easy comprehension. The Oort cloud begins roughly 5,000 times farther from our star than Earth orbits. It extends outward to perhaps 100,000 times Earth's distance. That span measures in trillions of miles. Light traveling at maximum speed would take more than 1 year to reach the cloud's inner edge. Crossing from one side to the other would consume over 1,000 years, even at light speed. Think about that time scale. Light left Earth 1,000 years ago when castles were being built in Europe. That ancient light would just now be emerging from the far side of the Oort cloud. The region is so vast that describing it in miles becomes meaningless. Only light years make sense, and even then the numbers numb the mind. Trillions of icy objects might populate the Oort cloud. Most measure somewhere between half a mile and 6 miles across. They orbit our star at such extreme distances that their paths become nearly circular despite barely feeling the star's gravity. Some objects take millions of years to complete one orbit. Time operates differently at these scales. The concept of a year loses meaning. Our star appears as just another point of light from the Oort cloud. No planets are visible without powerful telescopes. Earth vanishes completely. Anyone standing on an Oort cloud object would see only stars in every direction. The familiar shapes of our system would be gone. Darkness and cold rule this region. Absolutely. Temperature in the Oort cloud hovers around 450 degrees, only a few degrees above absolute zero. At that temperature, molecular motion almost stops. Chemical reactions cannot occur. Nothing melts, nothing evaporates, nothing changes. These objects exist in a frozen state that might preserve conditions from when our system formed billions of years ago. Occasionally, passing stars disturb the Oort cloud. Their gravity tugs on objects, altering orbits slightly. Some objects get nudged inward toward our star. These begin the long fall through the system. Millions of years later, they arrive near our star and becomes. The tails we see are ice vaporizing under starlight. By the time a comet appears in our sky, it has traveled farther than Voyager and taken longer than recorded history. No spacecraft has ever come close to reaching the Oort cloud. Voyager 1, humanity's most distant probe, would need 30,000 years to reach the inner edge. Pioneer 10 and Pioneer 11, the other distant spacecraft, face similar timescales. We have no technology capable of reaching the cloud within human lifetimes. Even if we launched a probe today using our best rockets, generations would pass before it arrived. The Oort cloud represents the true boundary of our star's influence. Beyond it, other stars exert comparable gravitational pull. Interstellar space begins in earnest. Our system becomes just one small bubble in a galaxy full of stars. The familiar ends. The alien begins. Mapping the odd cloud remains impossible with current technology. Objects there reflect almost no light. They are too small, too dark, and too distant to detect directly. We infer their existence from comet trajectories and mathematical models, but direct observation may never happen. The cloud might remain forever theoretical, accepted on faith rather than evidence. Consider the volume of space the Oort cloud occupies. If our system were the size of a coin, the Oort cloud would extend beyond a football field in all directions. The distances involved make the planet seem crowded by comparison. Everything familiar to us, every planet, moon, asteroid, occupies a tiny region at the center. The Oort cloud dwarfs all of it. Our star formed from a collapsing cloud of gas and dust. The Oort cloud objects are leftovers from that formation process, flung outward by gravitational interactions. They settled into stable orbits at the very edge of our star's gravitational reach. They will remain there until other stars disturb them or our star dies billions of years from now. Beyond the Oort cloud, true interstellar space stretches in every direction. The nearest star system waits across a void that makes everything we have discussed seem trivial. Alpha Centauri shines in the southern sky as one of the brightest stars visible from Earth. It appears as a single point to the naked eye, but telescopes reveal it as a system of 3 stars orbiting each other. This stellar neighborhood sits closer to us than any other star system. That proximity does nothing to make the journey manageable. 25 trillion miles separate us from Alpha Centauri. Light takes 4.3 years to cross that gap. That makes Alpha Centauri our nearest stellar neighbor. Yet the distance remains so vast that conventional spacecraft would need tens of thousands of years to arrive. Voyager 1, traveling at 38,000 mph, would require over 70,000 years to reach it. Human generations span roughly 25 to 30 years. In 70,000 years, between 2,000 and 3,000 generations would pass. Imagine launching a spacecraft today, knowing your descendants 2,000 generations later might see it arrive. The Great Pyramids were built only 200 generations ago. Written language emerged 300 generations back. Modern humans existed for maybe 10,000 generations total. A journey to Alpha Centauri requires rethinking what space travel means. No one alive at launch would live to see arrival. No one's children or grandchildren or great-grandchildren to any degree would witness the destination. The mission would outlast civilizations. Languages would evolve and die. Technologies would be invented, become obsolete, and be forgotten. The spacecraft would continue its silent journey through all of it. Engineers have proposed generation ships, massive vessels designed to support entire communities for millennia. People would be born, live, and die aboard these ships. Multiple generations would exist only in transit, never knowing Earth except through stories and records. The psychological challenges alone seem insurmountable. How do you maintain culture, purpose, and mental health across thousands of years in a closed system? Other proposals suggest suspended animation or frozen embryos. Put passengers in stasis, wake them on arrival, store genetic material and artificial wombs, grow people at the destination. These solutions avoid the generation ship problem, but introduce new ones. What happens if the technology fails? Can stasis be maintained for tens of thousands of years? Will anyone remember how to revive the passengers? Speed is the fundamental problem. Getting to Alpha Centauri in human lifetimes requires accelerating to significant fractions of light speed, but accelerating mass to those velocities demands energy that exceeds anything we can currently produce. Even a small spacecraft weighing a few tons would need power equivalent to detonating multiple nuclear bombs just to reach 10% of light speed. Breakthrough Starshot, a modern proposal, suggests using powerful lasers to push tiny light sail probes toward Alpha Centauri. These probes would weigh only g, carry minimal instruments, and rely on laser beams from Earth to accelerate them. Even this optimistic design estimates 20 to 30 years for the journey, but the probes could not slow down. They would scream past Alpha Centauri at tremendous speed, gathering data for only a brief window before disappearing into deep space. Alpha Centauri itself consists of three stars. Alpha Centauri A and B orbit each other, forming a binary pair. Proxima Centauri, a dim red dwarf, orbits the binary pair at a great distance. Proxima sits slightly closer to us than its companions, making it technically our nearest stellar neighbor. But the difference amounts to mere weeks at light speed. For practical purposes, the system acts as one target. Proxima Centauri hosts at least one confirmed planet, Proxima b, orbiting within the star's habitable zone. Liquid water could theoretically exist on its surface, but Proxima is a red dwarf prone to violent flares. These eruptions bathe the planet in radiation. Life, if it exists there, would face challenges Earth life never encountered. Still, the possibility drives interest. Our nearest potentially habitable world waits at the edge of what we might reach with technology that does not yet exist. The void between our star and Alpha Centauri contains almost nothing. No rest stops, no resources, just vacuum, stray hydrogen atoms, and cosmic rays. Any spacecraft making the journey would be utterly alone for the duration. If something broke, no repair mission could help. The crew would solve problems themselves or fail. Earth would be too far away to offer anything but sympathy, delayed by years. Standing on Earth and looking toward Alpha Centauri, you see the system as it was 4.3 years ago. The light entering your eye left those stars before the previous presidential election. Events happening there right now will not be visible until years from now. Distance creates a time barrier that technology cannot overcome. Even messages travel at light speed, limited by physics. But Alpha Centauri, impossibly far as it is, represents only one star among billions. Others sit much farther away across voids that make this journey look easy. Betelgeuse blazes red in the constellation Orion, visible from Earth as one of the brightest stars in the night sky. This red supergiant sits roughly 550 light-years away. The light you see tonight left that star 550 years ago, around the time Columbus sailed to the Americas. What Betelgeuse looks like right now, you will not know for another 550 years. This star nears the end of its life. Red supergiants burn through their fuel rapidly, exhausting nuclear fusion elements at an accelerating pace. Betelgeuse has already consumed most of its hydrogen and helium. It now fuses heavier elements deep in its core. Each new element burns faster than the last. The star races toward a catastrophic end. When Betelgeuse finally explodes as a supernova, the blast will briefly outshine every other star in its region of the galaxy. For a few weeks, Betelgeuse might appear as bright as the moon in Earth's sky. The explosion will be visible during daytime. Then slowly the light will fade as the expanding debris cloud cools and disperses. But here is the unsettling part. That explosion might have already happened. Betelgeuse could have detonated 500 years ago, and the light from the blast is still crossing the void toward us. Or it might explode tomorrow, and we will not see it until the year 2574. The distance creates a blindness. We observe only the past. The present remains hidden. Scientists monitor Betelgeuse closely for signs of the impending explosion. In late 2019 and early 2020, the star dimmed significantly. Speculation ran wild that the supernova had begun. Telescopes worldwide pointed at Betelgeuse, gathering data. Then the star brightened again. The dimming turned out to be dust clouds ejected from the star's surface, temporarily blocking light. The explosion had not started yet. Betelgeuse fluctuates naturally. Red supergiants pulsate, changing size and brightness over periods of months or years. Dust storms on stellar scales create temporary dimming. The star's outer layers constantly churn and change. Predicting the exact moment of explosion remains impossible. It could happen tonight. it could wait another 100,000 years. Stellar timescales mock human patience. The explosion itself will release more energy in seconds than our star emits in its entire lifetime. The blast wave will rip through Betelgeuse's outer layers at millions of miles an hour. Temperature will spike to billions of degrees. Heavy elements forged in the star's core will scatter into space. Carbon, oxygen, iron, gold, all the building blocks of planets and life will be thrown outward to eventually form new stars and worlds. Earth sits far enough away that the supernova poses no danger. 550 light-year provides comfortable distance. The explosion will not sterilize our planet or strip away the atmosphere. We will witness a spectacular light show, nothing more. Future generations might see Betelgeuse shining bright, then watch it fade over months, eventually disappearing from the night sky entirely. The explosion will leave behind a neutron star or black hole. All of Betelgeuse's mass will collapse into an object maybe 12 mir across. Gravity will become so intense that nothing, not even light, can escape the immediate vicinity. What once was a star larger than Jupiter's orbit will compress into a point smaller than a city. Astronomers have observed other supernovae in distant galaxies. Telescopes capture them regularly. Each explosion provides data about how stars die, but Betelgeuse offers something special. It will explode close enough that we can study the event in detail. Every wavelength of light from radio to gamma rays will be monitored. The data will improve our understanding of supergiant star death and element formation. Ancient civilizations might have witnessed Betelgeuse explode if it happened around 550 years ago. Mayan or Aztec astronomers could have recorded the event, but no historical accounts match the expected brightness and timing. This suggests either the star has not yet exploded or the explosion happened earlier and its light has not arrived. The uncertainty haunts researchers. Betelgeuse represents only one dying star among countless others. Red supergiants across the galaxy approach their ends. Some will explode soon by cosmic standards. Others wait for millions of years. Each one marks a region of space where new elements will form, where future systems will build from the remnants. The delay between explosion and observation reminds us how disconnected we are from distant events. We see the universe in layers of time. Nearby objects appear nearly current. Distant objects show us ancient history. Betelgeuse exists somewhere between, close enough to seem real, far enough that we observe with a 550-year lag. Another supernova remnant already visible in our sky tells a story of destruction frozen in time. In the year 1054, Chinese astronomers recorded a new star appearing in the daytime sky. It shone bright enough to cast shadows at night and remained visible for 23 days during daylight. Arab and Japanese astronomers also documented the event. Then slowly the star faded. Within 2 years, it vanished from view entirely. No one knew what they had witnessed. Nearly 700 years later, astronomers using telescopes discovered a strange glowing cloud in the same region of sky. The cloud had an irregular shape with filaments stretching outward like tentacles. They named it the Crab Nebula because early drawings vaguely resembled a crab. That cloud turned out to be the remains of the star that exploded in 1054. The Crab Nebula sits roughly 6,500 light-years from Earth. The supernova that created it actually occurred 6,500 years before 1054. The explosion happened around 5,500 years before humans built the pyramids. But light from the blast took 6,500 years to cross space. When it finally arrived in 1054, people on Earth saw a star die in real time, watching an event that finished thousands of years earlier. The nebula continues expanding today. The explosion hurled gas and debris outward at millions of miles an hour. That material has now spread across 11 light-years of space and keeps moving. The cloud grows larger every year, visible even in amateur telescopes. By measuring its expansion rate and working backward, astronomers confirmed the explosion date matches historical records. At the center of the Crab Nebula sits something stranger than the explosion itself. A pulsar, the crushed core of the dead star, spins 30 times per second. This neutron star contains more mass than our star, compressed into a sphere only 12 meters across. Gravity on its surface exceeds anything found on Earth by factors of billions. A teaspoon of neutron star material would weigh as much as a mountain. The pulsar emits beams of radiation from its magnetic poles. As it spins, these beams sweep across space like lighthouse beams. Earth sits in the path of one beam, so we detect a pulse 30 times every second. The regularity is so precise that early astronomers thought they might be receiving signals from an alien civilization. The truth proved even more incredible. They had discovered a new type of stellar remnant. The Crab pulsar powers the entire nebula. Its intense magnetic field and rapid rotation generate massive amounts of energy. That energy pumps into the surrounding gas, making it glow. Without the pulsar's energy, the nebula would fade over time. Instead, it remains one of the brightest objects of its type in our galaxy. Filaments within the nebula contain heavy elements forged in the star before it exploded. Oxygen, silicon, sulfur, and iron spread through the cloud. These elements will eventually mix with interstellar gas. Future stars will form from that enriched material. Planets might coalesce around those stars. Life could emerge on those planets built from atoms created in the Crab Nebula supernova. The nebula glows in multiple wavelengths. Visible light reveals red and blue filaments. X-rays show the pulsar and its wind of high-energy particles. Radio waves map the magnetic fields threading through the gas. Each wavelength reveals different aspects of the explosion and its aftermath. Astronomers combine these views to build a complete picture of what happens when a massive star dies. Comparing photographs taken decades apart shows the nebula's expansion clearly. Filaments stretch farther, the cloud grows, the pulsar remains at the center, barely moving, while debris races outward. The explosion released so much energy that the expanding gas will continue for thousands of years before slowing significantly. Other supernova remnants exist throughout our galaxy. Some are older than the Crab Nebula, their expanding shells now faint and stretched thin. Others are younger, still glowing bright from recent explosions. Each one marks a spot where a massive star exhausted its fuel and collapsed. Each one enriches the galaxy with heavy elements. Each one demonstrates the violent cycles of stellar life. The Crab Nebula offers a snapshot of destruction frozen in time. The star that exploded finished dying millennia ago, but the light and debris still spread outward. We observe the event in progress, watching an explosion unfold across centuries. What looks violent to us already happened in the distant past. Time and space twist together, making now and then difficult to separate. While some regions of space show death and destruction, others reveal birth on an equally massive scale. Deep in the Orion Nebula, 1,700 light-years from Earth, gas and dust collapse under their own gravity. This stellar nursery stretches 24 light-years across, glowing with the light of newborn stars. Thousands of stars form inside this cloud. While you watch over a human lifetime, new stars ignite. The process continues constantly, turning ancient material into fresh stellar furnaces. Stellar nurseries begin as cold, dark molecular clouds. Hydrogen gas and dust particles float together, held loosely by mutual gravity. Something triggers collapse. Perhaps a nearby supernova sends a shockwave through the cloud. Perhaps two clouds collide. Whatever the cause, regions within the cloud begin contracting. As gas falls inward, it heats up. Friction between particles converts gravitational energy into thermal energy. The center of the collapsing region grows hotter and denser. Pressure builds. Eventually, temperature and pressure reach the point where hydrogen atoms fuse into helium. Nuclear fusion ignites. A star is born. The process takes millions of years for large stars, longer for small ones. But stellar nurseries contain hundreds or thousands of collapsing regions simultaneously. While one star forms slowly, others reach ignition. The nursery produces stars on an assembly line. New lights appear in the cloud. Constantly, young stars blast their surroundings with intense radiation and powerful winds. This energy carves out cavities in the surrounding gas. The cloud begins to glow, illuminated from within by its newborn stars. Hubble Space Telescope images of stellar nurseries show intricate structures. Pillars of gas resist erosion. Cavities expand where young stars have cleared space. Shock waves ripple through the cloud. The Eagle Nebula contains one of the most famous stellar nurseries. The pillars of creation, photographed by Hubble, show towering columns of gas where stars currently form. Each pillar stretches several light years long. At their tips, dense knots of material collapse into new stars. The pillars themselves slowly evaporate as nearby massive stars blast them with radiation. Not all collapsing regions successfully form stars. Some lack enough mass. They become brown dwarfs, failed stars too small to sustain fusion. Others form in binary or multiple star systems, sharing material and orbits. The variety of outcomes depends on local conditions within the nursery. Mass, rotation, magnetic fields, and nearby objects all influence how stars develop. Material left over from star formation often forms planets. Dust particles in the disks surrounding a young star stick together through static electricity and gentle collisions. These clumps grow into pebbles, then boulders, then planetimals. Eventually, planets coalesce from the debris. Our own system formed this way roughly 412 billion years ago in a nursery long since dispersed. Astronomers observe stellar nurseries across the galaxy. Some lie nearby, easily studied with telescopes. Others hide behind dust clouds that block visible light. Infrared observations penetrate that dust, revealing the hidden stars within. Radio telescopes map the gas molecules. Each wavelength provides different information about star formation. The Carina Nebula, 8,500 light-years away, hosts some of the most massive stars ever discovered. These giants formed recently in cosmic terms, within the last few million years. They burn incredibly bright and will exhaust their fuel within 10 million years. Smaller stars form alongside them, destined to outlive the giants by billions of years. Star formation enriches the galaxy. Each generation of stars produces heavy elements through fusion. When massive stars explode, they scatter those elements into space. New nurseries incorporate these elements. Later generations of stars contain more heavy elements than earlier ones. This process gradually transforms the galaxy's composition. Our star formed from material enriched by previous stellar generations. The iron in your blood, the calcium in your bones, the oxygen you breathe, all originated in stars that exploded before our system existed. You are made of stardust, assembled from atoms forged in ancient stellar nurseries and scattered by supernovae. Stellar nurseries operate throughout the galaxy. The Milky Way produces roughly 3 new stars every year on average. That rate fluctuates based on available gas and recent disturbances, but over billions of years, star formation continues. The galaxy constantly recycles material, building new stars from old. Not all regions form stars. Some gas clouds remain stable. Others disperse before collapse begins. Star formation requires specific conditions. Too little density and gravity cannot overcome gas pressure. Too much turbulence and collapsing regions tear apart. The balance must be precise. Young stars often cluster together. Open clusters contain hundreds to thousands of stars born from the same nursery. These stars share similar ages and compositions. Over time, gravitational interactions disperse the cluster. Stars drift apart, eventually spreading across the galaxy. But for millions of years, they remain together, siblings from the same stellar family. The process playing out in stellar nurseries connects to everything that comes after. Stars power galaxies. They create heavy elements. They host planets. They make life possible. Without star formation, galaxies would dim and die. The universe would darken as existing stars exhausted their fuel. At the heart of our galaxy, where millions of stars orbit in a dense cluster, something far more powerful than any star commands attention, 26,000 light-years from Earth. At the exact center of the Milky Way, a supermassive black hole lurks, Sagittarius. A star contains 4 million times the mass of our star compressed into a region smaller than our star's orbit. Gravity near this monster becomes so intense that space itself warps dramatically. Matter falling toward it accelerates to significant fractions of light speed before crossing the event horizon and disappearing forever. You cannot see a black hole directly. No light escapes once matter crosses the event horizon, but you can observe the effects. Stars orbit Sagittarius, a star, at tremendous speeds. Astronomers have tracked individual stars circling the black hole for decades. These stars move so fast that their motion becomes visible over just a few years. One star, designated S2, orbits the black hole every 16 years. At closest approach, it reaches 5% of light speed. Watching S2 orbit Sagittarius. A star confirms Einstein's predictions about gravity. The star's path curves more sharply than Newton's laws predict. Space warps near the black hole, bending the star's trajectory. Light from the star shifts to redder wavelengths as it climbs out of the gravitational well. These observations prove that supermassive black holes exist and behave exactly as theory predicts. The black hole occasionally feeds. Gas and dust drift too close, pulled by gravity. As material spirals inward, friction heats it to millions of degrees. The superheated gas emits X-rays and radio waves before crossing the event horizon. Telescopes detect these emissions as flares lasting minutes to hours. Between feeding events, Sagittarius A star remains relatively quiet, but the black hole never stops pulling. Anything that wanders too close will eventually fall in. Stars venture dangerously near the black hole. Some pass within a few billion miles of the event horizon. Tidal forces at that distance stretch objects vertically while crushing them horizontally. A star unlucky enough to pass too close would be torn apart by these tidal forces. The debris would form an accretion disk around the black hole, gradually spiraling inward and disappearing. The Event Horizon Telescope captured the first image of Sagittarius A star's shadow in 2022. Multiple radio telescopes across Earth combined their observations to create a telescope effectively the size of the planet. The image showed a dark circle surrounded by glowing matter. That dark circle marks the event horizon, the point of no return. Anything crossing it can never escape, never send information back, never return. The event horizon of Sagittarius A star measures roughly 15 million miles across. That sounds large until you remember it contains 4 million stellar masses. The density exceeds comprehension. All that mass compressed into such a small volume creates a gravitational field so strong that physics begins to break down. Time slows near the event horizon. Space curves back on itself. Quantum effects dominate at scales where general relativity predicts singularities. How supermassive black holes form remains partially mysterious. They might grow from smaller black holes that merge and accumulate matter. They might form directly from collapsing gas clouds in the early universe. Evidence suggests they existed when galaxies were young, perhaps even before galaxies fully formed. Their presence might have helped galaxies develop structure by providing gravitational anchors. Nearly every large galaxy contains a supermassive black hole at its center. Some exceed billions of times our star's mass. These monsters dominate their galactic cores, influencing star formation and gas dynamics across thousands of light years. Their gravity helps shape galaxy evolution over billions of years. Sagittarius A star remains relatively quiet compared to other galactic centers. Some supermassive black holes devour matter, constantly creating brilliant quasars, visible across billions of light years. These active galactic nuclei outshine their entire galaxies. Sagittarius, a star feed, sporadically producing occasional flares, but no sustained emission. Our galaxy's black hole sits dormant most of the time. The black hole does not suck everything nearby into oblivion. Objects in stable orbits remain safe. The Milky Way stars orbit the galactic center without spiraling inward. Only material that loses angular momentum or passes too close faces destruction. The black hole influences the galaxy's structure, but it does not actively hunt down distant objects. Light from stars near Sagittarius. A star takes 26,000 years to reach Earth. We see the galactic center as it was when Neanderthals walked Europe. The stars orbiting there right now follow paths we will not observe until 26,000 years from now. Distance creates this delay, forcing us to study the past while the present remains hidden. Understanding what happens inside the event horizon requires physics we do not yet possess. General relativity predicts singularities where density becomes infinite. Quantum mechanics suggests something else might occur. The two theories conflict at the scales where black holes compress matter. Resolving this conflict remains one of physics' great challenges. Our entire galaxy orbits around Sagittarius A star. Hundreds of billions of stars follow vast, curved paths through space, held together by mutual gravity with the black hole at the center. Right now, Earth races through space at speeds that dwarf any velocity you have experienced. Our planet orbits our star at $67,000 mph. Our star orbits the galactic center at $490,000 mph. You feel none of this motion, no wind, no resistance, just smooth gliding through vacuum while the galaxy rotates beneath us. The Milky Way spans 100,000 light-years from edge to edge. Our star sits 26,000 light-years from the center, about halfway out in a spiral arm. At our current speed, we complete one orbit around the galactic core every 230 million years. The last time Earth occupied this spot in the galaxy, dinosaurs had not yet evolved. Reptiles were just beginning to dominate the land. 230 million years is called a galactic year or cosmic year. Earth has completed roughly 20 galactic years since it formed. Each orbit takes our star on a vast circuit through space, passing near other stars and gas clouds. Sometimes these encounters trigger star formation. Sometimes they disrupt planetary systems. The galaxy constantly churns and reorganizes itself. Our star moves relative to nearby stars. While we all orbit the galactic center, each star follows a slightly different path at a slightly different speed. Stars pass each other like cars on a highway, some overtaking us while we overtake others. The relative motion creates a complex dance that plays out over millions of years. The spiral arms we see in the Milky Way are not fixed structures. They represent density waves moving through the galaxy. Stars and gas enter the spiral arms, slow down slightly due to increased density, then exit on the other side. The arms themselves rotate more slowly than individual stars. This creates the spiral pattern without requiring matter to stay locked in place. Our star entered a spiral arm roughly 10 million years ago. We will exit it in about 10 million more years. Spiral arms concentrate gas and trigger star formation. While we transit through, the density of nearby objects increases slightly, but space remains mostly empty even in these denser regions. The increased risk of collisions remains negligible. Gravity from Sagittarius, a star, holds the galaxy together, but the black hole alone lacks enough mass. Dark matter provides most of the gravitational binding. An invisible halo surrounds the galaxy containing 5 times more mass than all visible stars combined. This dark matter does not emit light and cannot be directly detected. We infer its existence from how galaxies rotate and how gravity bends light passing near them. Without dark matter, galaxies would fly apart. Stars in the outer regions orbit too fast to remain bound by visible matter alone. Something unseen adds extra gravity. That something is dark matter. Its nature remains one of astronomy's greatest mysteries. We know it exists, we measure its effects, but we do not know what particles or fields comprise it. The galaxy rotates differentially. Inner regions complete orbits faster than outer regions. This differential rotation winds the spiral arms tighter over time. Eventually, the arms would blur and disappear if nothing counteracted the process. Density waves and gravitational interactions with nearby galaxies maintain the spiral structure despite this winding effect. Other galaxies orbit outside the Milky Way. Dozens of small dwarf galaxies circle our galaxy like moons around a planet. The Magellanic Clouds visible from the southern hemisphere are two such satellites. They orbit the Milky Way, held by gravity, slowly being torn apart by tidal forces. Eventually, they will merge with us, adding their stars to the galactic population. The galaxy moves through space as a whole. It falls toward the Virgo cluster, an enormous collection of galaxies. That motion adds another layer to our velocity. Earth moves relative to our star. Our star moves relative to the galactic center. The galaxy moves relative to the Virgo cluster. All these motions combine. The result is a complex path through space that changes depending on your reference frame. Ancient peoples believed the stars were fixed to a celestial sphere. They tracked planets moving against the stellar background, but they assumed stars themselves remained stationary. Only with precise measurements did we discover stellar motions. Then we learned those motions arose from galactic rotation. Each discovery revealed a larger scale of motion. The universe operates in constant flux. Nothing stays still. Our rapid orbit through the galaxy creates a kind of stability. The motion prevents us from falling toward the galactic center. We remain in equilibrium, balanced between gravity pulling inward and angular momentum carrying us forward. That balance sustains our position in space. Standing on Earth, you cannot feel this motion. The planet spins on its axis, orbits our star, and races through the galaxy all simultaneously. Yet you experience none of it directly. Only careful observations reveal the truth. We exist in perpetual motion through space, blind to our own speed. Surrounding our star, surrounding us, stretches a bubble carved by ancient violence. Our star floats inside a cavity carved by violence. The local bubble stretches roughly 1,000 light-years across, a region of space where gas density drops to 1/10th of normal levels. We sit near the center of this void, surrounded by walls of compressed gas that mark where ancient supernovae shocked their surroundings. The bubble exists as a monument to stellar death, a scar left by explosions that occurred millions of years ago. Multiple supernovae created this structure. Between 10 and 20 million years ago, massive stars in our region reached the end of their lives. They exploded in succession, each blast pushing gas and dust outward. The expanding shock waves merged, hollowing out a vast cavity. The explosion scattered the dense material that once filled this volume, leaving behind thin, hot gas heated to millions of degrees. Temperature inside the local bubble reaches around 1 million grime. That sounds impossibly hot, and it is, but gas density drops so low that you would freeze rather than burn if you floated inside it. Heat is energy per particle. Temperature measures average particle velocity. In extremely low-density gas, few particles exist to transfer that energy. Each particle moves fast, but collisions happen rarely. The bubble's walls glow faintly in X-rays. Hot gas emits high-energy radiation. Telescopes designed to detect X-rays map the bubble structure. They reveal a somewhat irregular shape, elongated in some directions and compressed in others. Interactions with nearby supernova remnants and gas clouds have deformed the bubble over time. Our star formed outside the local bubble. We entered it roughly 5 million years ago. Our motion through the galaxy carried us across the bubble wall and into the cavity. We will eventually exit on the other side in another few million years. Entering the bubble changed the environment around our system. Interstellar gas density dropped. Cosmic ray intensity altered. The shift might have influenced Earth's climate or biosphere in ways we barely understand. Stellar nurseries avoid bubbles. Star formation requires dense gas. The local bubble contains too little material to form stars. Its walls, however, compress gas and might trigger new star formation. Where expanding bubbles collide with dense clouds, they squeeze material together. Gravity then takes over, leading to new stellar births. The bubble simultaneously destroys and creates, clearing regions while concentrating material elsewhere. Similar bubbles exist throughout the galaxy. Wherever massive stars cluster together, their eventual explosions carve cavities. Some bubbles merge into superb spanning thousands of light years. These giant structures shape the galaxy's appearance and influence how it evolves. They drive turbulence in interstellar gas and help regulate star formation rates. The local bubble connects to other nearby bubbles. The Scosan complex, a region of young stars and gas, borders our bubble. Its own supernova contribute to shaping the environment. The boundary between bubbles shifts and blurs. Gas flows from one cavity to another. Material cycles through these structures over millions of years. Cosmic rays behave differently inside bubbles. These high-energy particles travel through space, occasionally striking Earth's atmosphere and creating showers of secondary particles. The local bubble's low density allows cosmic rays to propagate farther without scattering. This might increase the cosmic ray flux Earth experiences. Some researchers speculate this could influence atmospheric chemistry or cloud formation. The evidence remains uncertain, but the possibility intrigues scientists. The bubble protects us in some ways. Dense interstellar clouds can block starlight and emit radiation. The local bubble's low density provides clear sight lines. Astronomers can observe distant objects without significant obscuration. This transparency benefits observations, but also exposes us to radiation from farther away. Mapping the local bubble required decades of work. Astronomers measured distances to nearby stars and gas clouds. They tracked the distribution of neutral hydrogen using radio telescopes. They analyzed X-ray emission from hot gas. Slowly, the bubble's shape and extent emerged from the data. We now know we live inside this structure, though details about its exact boundaries and history remain unclear. The bubble reminds us that space is not empty and uniform. Regions differ dramatically in temperature, density, and composition. Our location within the galaxy influences what we observe and perhaps even planetary conditions. We orbit through a dynamic galaxy where supernova remnants, gas clouds, and stellar winds create ever-changing environments. But our galaxy is not alone. Another massive spiral galaxy barrels toward us through the darkness. 2.12 million light-years away, the Andromeda Galaxy dominates the night sky of its local region. This massive spiral contains roughly 1 trillion stars, dwarfing our Milky Way's few hundred billion. Andromeda appears as a faint smudge to the naked eye from Earth, deceptively peaceful. That appearance hides a terrifying truth. Andromeda rushes toward us at 75 ms. The collision is inevitable. In roughly 4 billion years, Andromeda will arrive. The two galaxies will slam together in a cosmic merger that reshapes both. Stars will not actually collide. Space between stars remains so vast that direct impacts are unlikely, but gravitational chaos will scatter stars across enormous distances. Our star might be flung into intergalactic space. It might plunge toward the merged galactic core. The stable orbit we currently enjoy will end. Computer simulations show how the merger will unfold. The galaxies will pass through each other during the first encounter. Tidal forces will stretch both spirals, creating long streamers of stars pulled into space. The galaxies will separate, slow down, then fall back together for a second pass. Multiple encounters over hundreds of millions of years will gradually merge the two systems into one giant elliptical galaxy. Earth will likely survive the merger intact. Distances between stars protect us from direct hits, but our position in the galaxy will change dramatically. We might orbit much farther from the new galactic center. We might sink closer to the core where star density increases. The night sky will transform. Familiar constellations will scatter. New patterns will emerge as stars from both galaxies intermingle. The merged galaxy has already been nicknamed Milomeda, or Milk Dromeda. It will contain nearly 2 trillion stars. Gas clouds will collide and compress, triggering massive bursts of star formation. The merger will create millions of new stars over a relatively short period. These stellar nurseries will light up the new galaxy with brilliant blue light from young hot stars. Black holes at the centers of both galaxies will eventually merge. Sagittarius A star will combine with Andromeda's supermassive black hole, creating a monster containing millions of stellar masses. The merger will release gravitational waves so powerful they would be detectable across billions of light years. But by the time this happens, no one on Earth will be around to observe it. Our star will die before the merger completes. In roughly 5 billion years, it will exhaust its hydrogen fuel and expand into a red giant. That expansion will likely vaporize Earth or at least render it uninhabitable. The galactic collision and stellar death occur on similar timescales. Humanity, if it still exists, will face both catastrophes within the same cosmic era. Andromeda currently approaches at 250,000 mph when you account for all relative motions. That sounds fast, but the distance remains so vast that the approach takes billions of years. Ancient light from Andromeda takes 2 and 12 million years to reach us. We see that galaxy as it was before modern humans evolved. The Andromeda of today remains hidden by distance and light-year delay. Other galaxies in the local group will participate in the merger. The Triangulum galaxy, third largest in our group, will likely join the collision. Smaller dwarf galaxies will be absorbed or flung into space. The entire local structure will reorganize itself around the new merged core. Watching the approach requires patience. Andromeda's motion across the sky is imperceptible over human lifetimes. Only precise measurements reveal the closing distance. Astronomers track individual stars in Andromeda to calculate velocity. The data leaves no doubt. The galaxies will merge. The timeline extends beyond anything humanity might witness, but the physics demands it. Galactic collisions happen throughout the universe. Hubble has photographed hundreds of merging galaxies at various stages. Some show initial contact. Others display dramatic tidal tails stretching millions of light years. Still others reveal nearly complete mergers with chaotic cores and scattered star fields. Andromeda and the Milky Way will follow this same path. The merger demonstrates that even galaxies are not permanent. Everything in the universe changes. Stars are born and die. Galaxies merge and evolve. The cosmos transforms itself across deep time. What seems eternal to us exists only temporarily on cosmic scales. But the Milky Way and Andromeda represent just two members of a larger family bound by gravity. Our galaxy does not drift alone through space. It belongs to a gravitationally bound collection called the local group. Roughly 50 galaxies orbit within this region, spanning 10 million light-year across. The Milky Way and Andromeda dominate as the two largest members. Everything else remains significantly smaller, dwarf galaxies containing only millions or billions of stars. The local group formed early in cosmic history. Gravity drew these galaxies together over billions of years. They orbit each other, interacting through tidal forces and occasional collisions. The structure represents a single gravitational unit. These galaxies share a common fate, bound together, while the rest of the universe expands away. The third largest member, the Triangulum galaxy, contains roughly 40 billion stars. It orbits as a satellite of Andromeda, though some evidence suggests it might be falling toward the Milky Way instead. The dynamics remain unclear. Three-body gravitational problems defy simple solutions. Triangulum will participate in the eventual merger, but exactly how remains uncertain. Beyond the big three, the local group contains dozens of dwarf galaxies. The large and small Magellanic clouds orbit the Milky Way, visible from the southern hemisphere as fuzzy patches. These irregular galaxies slowly spiral inward, torn apart by tidal forces. Eventually, they will merge with our galaxy, adding their stars to the Milky Way's population. Other dwarf galaxies scatter throughout the local group. Sculptor, Fornax, Leo Foire, and many others orbit the larger galaxies like moons around planets. Some are sporidal, lacking clear structure. Others maintain irregular shapes. All of them contain far fewer stars than major galaxies. The smallest known dwarf galaxies hold only a few thousand stars, barely qualifying as galaxies at all. These dwarf galaxies pose problems for current cosmological models. Simulations predict thousands of small galaxies should orbit the Milky Way and Andromeda. Observations find only dozens. This missing satellite problem suggests either simulations overestimate dwarf galaxy formation or most dwarf galaxies are too dark to detect. Dark matter might dominate them so completely that stars barely exist. Some local group members hide behind the Milky Way's disk. Dust and stars block our view in certain directions. Astronomers call this the zone of avoidance. Galaxies might lurk there, invisible to current surveys. Only by observing in wavelengths that penetrate dust or by waiting for the Milky Way to rotate enough to clear the view can we map this obscured region. The local group's total mass exceeds 2 trillion times our star's mass. Most of that mass sits invisible as dark matter. The 50 visible galaxies represent only a fraction of the gravitational binding. Dark matter halos extend far beyond visible stars, creating a web of gravity that holds the group together. Motion within the local group shows complexity. Galaxies do not orbit in neat circles. They follow elongated paths, sometimes approaching, sometimes receding. Gravitational interactions between members perturb orbits constantly. The system achieves dynamic equilibrium, but individual galaxies wander through complicated trajectories. The local group sits near the edge of a much larger structure. The Virgo cluster, containing thousands of galaxies, dominates the region beyond. The local group falls toward Virgo, pulled by its combined gravity. That infall adds another layer to our motion, our cosmic address. We orbit our galactic center. Our galaxy moves within the local group. The local group falls toward Virgo. Measuring distances to local group galaxies required decades of work. Astronomers use Cepheid variable stars whose brightness fluctuates predictably based on their period. By comparing apparent brightness to known luminosity, distances could be calculated. Later, other methods refined the measurements. We now know the local group's extent and member positions with reasonable accuracy. The group's boundaries blur at the edges. Defining exactly where the local group ends and intergalactic space begins depends on somewhat arbitrary criteria. Galaxies near the boundary might be falling toward the group or drifting away. Their status remains ambiguous until better data clarifies their motion. Interactions within the local group trigger star formation in some members. When dwarf galaxies pass through the halos of larger galaxies, gas compresses and collapses into stars. The Magellanic clouds experience such triggered star formation as they interacted with the Milky Way. Streams of stars pulled from the clouds trace their orbital path. Our position within the local group provides a unique perspective. We orbit one of the dominant galaxies. We see Andromeda approaching. We observe dwarf galaxies orbiting both major spirals. This vantage point lets us study galactic interactions up close. Other civilizations in distant galaxy groups might observe their own local dynamics, but we study ours. The local group will not remain distinct forever. As it falls toward Virgo, it might eventually merge with larger structures. The boundaries defining our group could dissolve. New gravitational configurations could emerge. The structure we observe today represents a temporary arrangement in cosmic evolution. But something beyond the local group pulls with irresistible force, dragging everything toward a hidden mass. Roughly 200 million light-years away, hidden behind the Milky Way's disk, something massive pulls on our local group. The Great Attractor exerts gravitational influence strong enough to drag millions of galaxies toward a single point. We cannot see this region directly. Dust and stars block our view, but we measure its effects through galaxy velocities. Everything in our region of the universe, including us, falls toward this invisible mass. The Great Attractor contains the equivalent of tens of thousands of galaxy masses concentrated in a relatively small region of space. That concentration creates a gravitational well deep enough to affect galaxy clusters hundreds of millions of light-years away. Our local group moves toward it at roughly 1/300,000 mph. We cannot resist. The pull operates over scales too vast for individual galaxy groups to counteract. Astronomers discovered the Great Attractor by mapping galaxy velocities. The universe expands, carrying galaxies away from each other, but local gravity creates deviations from smooth expansion. By measuring these deviations, astronomers traced motion patterns. Multiple galaxy clusters all moved in the same direction toward a point hidden behind the Milky Way's zone of avoidance. The region contains the Norma cluster, a massive collection of galaxies partially visible through gaps in the dust. But the Norma cluster alone does not account for the observed gravitational pull. Something larger exists there, either concentrations of dark matter we cannot detect or additional galaxy clusters hidden by dust. X-ray observations have revealed some hidden clusters by detecting hot gas between galaxies. Those clusters contribute to the total mass, but questions remain. Later surveys suggested the Great Attractor itself falls towards something even larger. The Shapley supercluster, containing thousands of galaxies, lies beyond the Great Attractor. Its mass dwarfs anything nearby. The Great Attractor might be only an intermediate waypoint in a much larger flow of galaxies toward Shapley. This raises the possibility of structures within structures, each pulling on smaller configurations. Gravity operates without barriers. Even though dust prevents us from seeing the Great Attractor clearly, its gravitational influence reaches across space unimpeded. We feel its pull despite the visual obstruction. This demonstrates how gravity differs from light. Photons scatter off dust particles. Gravitational fields propagate through empty space and matter equally. The existence of the Great Attractor challenges our understanding of cosmic structure. Early models predicted more uniform distribution of matter. Large concentrations like the Great Attractor were not expected in certain cosmological frameworks. Their discovery forced revisions to how we model structure formation. Dark matter clustering, initial density fluctuations, and gravitational collapse must be reassessed to explain what we observe. Our motion toward the Great Attractor combines with other motions. We orbit the Milky Way's center. The Milky Way moves within the local group. The local group falls toward the Virgo cluster. All of these motions add to our velocity toward the Great Attractor. Disentangling these components requires careful measurement and modeling. Each layer of motion reveals another level of cosmic structure. The term Great Attractor has sparked public imagination. It sounds ominous, as if some cosmic drain pulls everything toward destruction. The reality is less dramatic. This is simply a region of enhanced mass density. Galaxies fall toward it because gravity works exactly as expected. No mystery physics operates here, just the familiar attraction of mass toward mass, operating at enormous scales. Will we eventually crash into the Great Attractor? No. The universe's expansion works against gravitational collapse at large scales. While the Great Attractor pulls us inward, space itself expands, carrying distant structures away. The two forces balance differently depending on distance. Nearby structures succumb to gravity and collapse. Distant structures recede faster than gravity can pull them back. The Great Attractor influences our local region, but it cannot overcome cosmic expansion globally. Mapping hidden structures behind the Milky Way requires creative techniques. Radio telescopes can penetrate dust better than optical instruments. Infrared observations reveal cool stars that visible light misses. Surveys using these wavelengths have gradually filled in the zone of avoidance. We now have a partial picture of what hides there, though details remain incomplete. The greater attractor sits within a larger framework of structure. Galaxy clusters organize into superclusters. Superclusters arrange along filaments. These filaments form a cosmic web that spans the observable universe. The Great Attractor represents one node in this web, a dense region where filaments intersect. Understanding it requires understanding the larger web. Beyond this localized pull, an even grander organization shapes how galaxies distribute themselves across space. Our galaxy resides within a vast structure that organizes roughly 100 galaxy groups and clusters. The Virgo supercluster spans 110 million light-year across and contains roughly 47,000 galaxies. These galaxies arrange themselves in a flattened disk shape dominated by the Virgo cluster near the center. The entire structure rotates slowly, though at scales so vast that one rotation takes hundreds of billions of years. The Virgo cluster itself contains over 1,000 galaxies, packed into a region only 15 million light-year across. By cosmic standards, that density qualifies as crowded. Galaxies interact frequently through gravitational encounters. Some merge, others pass close enough that tidal forces strip away stars and gas. The cluster core glows with combined starlight from hundreds of giant elliptical galaxies. At the center of the Virgo cluster sits Messiah 87, a supergiant elliptical galaxy. This monster contains roughly 1 trillion stars and hosts a black hole billions of times more massive than our star. The Event Horizon Telescope photographed this black hole in 2019, producing the first direct image of an event horizon. The photo showed a glowing ring of matter surrounding a dark central shadow. That shadow marks where light cannot escape. Our local group orbits on the outskirts of the Virgo supercluster. We sit roughly 65 million light-years from the Virgo cluster center. Gravity from the cluster pulls on us, affecting our motion through space. We fall toward Virgo at hundreds of miles s. Eventually, over billions of years, the local group might be absorbed into the Virgo cluster unless cosmic expansion prevents the merger. The supercluster structure arose from tiny density fluctuations in the early universe. Regions slightly denser than average attracted more matter through gravity. Over billions of years, these enhancements grew. Matter flowed into overdense regions while emptying from underdense areas. The result is the cosmic web we observe today, with dense clusters connected by filaments and separated by voids. Superclusters do not qualify as gravitationally bound structures. Expansion of the universe works against gravitational collapse at these scales. Individual galaxy clusters within the supercluster remain bound, but the supercluster as a whole expands along with cosmic expansion. The structure represents a transitional scale between bound and unbound. Gravity influences motion, but cannot prevent the overall expansion. Mapping the Virgo supercluster required surveys of galaxy red shifts. As the universe expands, light from distant galaxies shifts toward longer, redder wavelengths. The amount of shift indicates distance. By measuring thousands of galaxy red shifts, astronomers constructed three-dimensional maps. These maps revealed how galaxies cluster and showed the supercluster's full extent. The Virgo supercluster is not unique. Thousands of similar superclusters fill the observable universe. They represent common structures at this scale. Some are larger, some smaller, some denser, some more diffuse, but all show similar organization. Dense clusters connected by filaments surrounded by voids. The pattern repeats across cosmic scales. Dark matter dominates supercluster mass. Visible galaxies represent only a small fraction of the total. Dark matter halos extend far beyond galaxy boundaries, creating a scaffolding that guides galaxy distribution. This invisible matter shapes structure formation and continues to influence how galaxies move. Without dark matter, superclusters could not exist. Normal matter alone lacks sufficient gravity to create these structures. X-ray observations reveal hot gas filling the space between galaxies and clusters. This intergalactic medium reaches temperatures of tens of millions of degrees. The gas glows brightly in X-rays, though it remains invisible to optical telescopes. That gas contains more ordinary matter than all the stars in cluster galaxies combined. Most atoms in clusters hide in this hot, diffuse medium. The Virgo supercluster represents our cosmic address at large scales. We orbit a star in the Milky Way. The Milky Way belongs to the local group. The local group exists within the Virgo supercluster. Each level encompasses the previous one. The hierarchy of structure organizes the universe from small to large, but recent discoveries reveal that the Virgo supercluster itself forms part of something even more immense. Our address extends farther than anyone suspected. In 2014, astronomers announced a discovery that redefined our cosmic address. The Virgo supercluster, long considered our largest gravitational structure, turned out to be only a small lobe of something vastly bigger. Linnea, meaning immeasurable heaven in Hawaiian, spans 520 million light-year across and contains 100,000 galaxies. This supercluster of superclusters represents our true home in the universe. Linnea was discovered by mapping galaxy flows. Galaxies do not simply recede due to cosmic expansion. Local gravity creates motions superimposed on that expansion. By carefully subtracting the expansion component from measured velocities, astronomers revealed how galaxies move due to gravity alone. Those motions flow like rivers converging toward basins of attraction. Linnea represents one such basin, a gravitational watershed containing everything that flows toward a common point. The boundary of Linnea is defined by where galaxy flows diverge. On one side, galaxies fall toward our basin of attraction. On the other side, they fall toward different basins. This dividing line marks the edge of our supercluster. The definition feels abstract, but it provides a clear physical way to delineate structure at these scales. Four major components make up Linnea. The Virgo supercluster forms one lobe. The Hydra-Orus supercluster, the Pavo-Indus supercluster, and the Southern supercluster complete the structure. These formally separate entities connect through tendrils of galaxies and dark matter. Together, they create a web of mass that spans hundreds of millions of light years. At the heart of Linnea lies the Great Attractor. Though it does not sit at the geometric center, galaxies flow toward this region from all directions. The Great Attractor serves as a focal point, though Linnea's structure extends far beyond it. The supercluster's full mass distribution, dominated by dark matter, creates a complex gravitational landscape that guides these flows. Linnea contains roughly 100 quadrillion times our star's mass. That number becomes meaningless without context. Think of it as 100,000 Milky Way-sized galaxies worth of mass. Even then, the scale defies intuition. This structure represents one of the largest coherent entities in the universe. The supercluster's shape appears irregular and elongated. It stretches across space like a cosmic highway with dense clusters marking major intersections. Filaments connect these clusters, forming a web. Voids separate the web strands, creating vast empty regions where few galaxies exist. This sponge-like structure characterizes matter distribution at cosmic scales. Linnea does not represent a bound structure. Cosmic expansion prevents gravitational collapse at these scales. The supercluster expands along with the universe. Galaxies within it move apart over time. Though their peculiar velocities create temporary convergence toward the Great Attractor, the structure marks a region of common motion, not a permanent gravitational system. Naming superclusters follows no strict rules. Astronomers often choose names based on constellations or cultural references. Lania honors the Polynesian navigators who used stars to cross the Pacific Ocean. The name reflects how mapping cosmic structures resembles navigating by celestial references. Both require careful observation and understanding of vast spaces. Other superclusters exist beyond Lania. The Shapley supercluster, even more massive, lies roughly 500 million light-year away. The Perseus-Pisces supercluster occupies a different region of space. Each represents a separate basin of gravitational attraction. Together, they make up the cosmic web at the largest observable scales. Lania's discovery demonstrates how our cosmic address keeps expanding. First, we learned Earth orbits our star. Then we understood our star orbits the galaxy. We discovered the local group, then the Virgo supercluster. Each revelation placed us within a larger context. Lania may not be the final layer. Future observations might reveal even grander structures organizing the universe. The supercluster's influence affects our motion through space. Every galaxy in Lania participates in flows shaped by the structure's mass distribution. We fall toward the great attractor because Lania's gravity demands it. Our trajectory through the cosmos is not random. It follows patterns determined by the largest structures in the universe. Understanding Laniakea required advanced computational techniques. Astronomers analyzed velocity data from thousands of galaxies. They developed models to separate expansion from gravitational motion. They visualized flows in 3 dimensions. The result revealed structure invisible to conventional observations. Lania existed all along. We simply lacked the tools to see it. The cosmic web extends far beyond Lania, organizing galaxies into filaments that stretch across the observable universe. Zoom out from Lania and a pattern emerges. Galaxies do not scatter randomly through space. They organize into filaments, vast chains of matter stretching hundreds of millions of light years. These cosmic threads connect galaxy clusters like beads on a string. Between them yawn enormous voids, regions containing almost nothing. The universe resembles a sponge or foam with matter concentrated in thin sheets and filaments surrounding empty bubbles. The largest filaments span over 1 billion light-year from end to end. Light takes 1 billion years to travel their length. These structures formed from quantum fluctuations in the early universe, amplified by billions of years of gravitational growth. Tiny density variations became towering walls and filaments as matter flowed toward overdense regions. The cosmic web formed gradually. In the early universe, matter distributed nearly uniformly, but tiny imperfections existed, variations at the level of 1 part in 100,000. Gravity amplified these variations. Denser regions pulled in nearby matter. Under dense regions emptied out over billions of years. The contrast increased. Dense regions collapsed into galaxies and clusters. Voids expanded and merged. The web took shape. Filaments contain galaxies, gas, and dark matter. Dark matter provides the gravitational scaffolding. Normal matter flows along dark matter filaments, collecting in nodes where they intersect. Those nodes become galaxy clusters. The filaments themselves host individual galaxies and galaxy groups strung along their length. Gas streams through filaments funneling material toward clusters. The gas in filaments reaches temperatures around 100,000 degrees. At those temperatures, hydrogen emits ultraviolet light. Telescopes designed to detect UV can map these filaments directly. The gas glows faintly, revealing the cosmic web structure. Most filament gas remains too diffuse to see with optical telescopes. Only specialized instruments detect its signature, void separate filaments rate. These regions contain few galaxies and little matter. Some voids span 300 million light-year across. If you placed yourself in the center of such a void, galaxies would appear only as faint smudges on the horizon. The nearest galaxy cluster might lie 150 million light-years away in any direction. You would float in almost perfect emptiness. Galaxies inside voids do exist, but rarely. These void galaxies tend to be small, isolated, and starved of gas. Without nearby galaxies to interact with, they evolve differently than galaxies in filaments or clusters. Star formation proceeds slowly. Merges never occur. Void galaxies represent cosmic hermits cut off from the busy regions where most galaxies cluster. The cosmic web extends throughout the observable universe. No matter which direction we look, we see the same pattern. Filaments, clusters, and voids repeat at all observable scales. This suggests the structure continues beyond what we can see. The universe likely displays similar organization far past the cosmic horizon. Simulating the cosmic web requires massive computational power. Astronomers run programs that track billions of dark matter particles across cosmic history. These simulations begin with conditions matching the early universe. Then they let gravity operate, watching structure grow over billions of simulated years. The results match observations remarkably well. Simulated webs look like the real cosmic web. One specific filament connects the Virgo supercluster to the Coma cluster. This bridge spans roughly 300 million light-year. Galaxies line its length with gas and dark matter filling the space between. The filament guides matter flow between the two clusters. Galaxies migrating along the filament eventually join one cluster or the other. Filaments slowly drain into clusters. Gravity from massive clusters pulls on filament material. Galaxies, gas, and dark matter slide along the web toward dense nodes. Over billions of years, filaments thin as their matter accretes onto clusters. The web gradually reorganizes itself, driven by gravity's relentless pull. The web's existence confirms predictions from cosmological theory. The standard model of cosmology, incorporating dark matter and dark energy, predicts exactly this type of structure. Observing it validates the model and provides confidence in our understanding of how the universe evolves. But one filament challenges everything we thought we knew about cosmic structure limits. 10 billion light-years away, a structure so massive it should not exist according to standard cosmology stretches across the sky. The Hercules Corona Borealis Great Wall spans roughly 10 billion light-year from end to end. This makes it the largest known structure in the observable universe. Its existence challenges fundamental assumptions about how the cosmos organizes itself at the largest scales. The Great Wall consists of galaxy clusters aligned along a filament. These clusters are not randomly scattered. They follow a coherent pattern extending across a significant fraction of the observable universe. The structure's discovery came from mapping gamma-ray bursts, the most powerful explosions in the universe after the Big Bang. These bursts cluster along the Great Wall, revealing its extent. Cosmological principle states that the universe should look roughly the same in all directions when viewed at large enough scales. Structures should not exceed a certain size limit. That limit sits around 1,200,000,000 light-year, based on how long gravity has had to organize matter since the Big Bang. The Hercules Corona Borealis Great Wall exceeds this limit by nearly 10 times. It is too large to exist, yet it exists. Observations confirm the structure. Multiple independent studies using different methods reach similar conclusions. The Great Wall is real. This creates a problem. Either our understanding of structure formation is incomplete or the cosmological principle requires modification. One possibility suggests the Great Wall is not a single coherent structure. Perhaps we see a projection effect, multiple unrelated structures aligned by chance along our line of sight. This would make the structure appear connected when actually it consists of separate pieces at different distances. Some astronomers favor this explanation. It preserves standard cosmology without requiring new physics. Another explanation proposes that structure formation worked differently in the early universe than current models predict. Maybe density fluctuations at certain scales were larger than we thought. This would allow bigger structures to form, but this requires adjusting initial conditions in ways that conflict with cosmic microwave background observations. The numbers do not easily reconcile. Dark matter distribution might differ from what simulations assume. If dark matter clumps more efficiently at large scales, it could build bigger structures, but no known dark matter model predicts this behavior. The particle physics required would differ substantially from current candidates. This path demands new physics with little supporting evidence. The Great Wall contains roughly 10 billion times our star's mass. That estimate remains uncertain due to measurement challenges. Determining exact mass distribution across 10 billion light-year requires extensive galaxy surveys and dark matter mapping. We see only a fraction of the total mass. Dark matter dominates but cannot be directly observed. Estimates rely on galaxy counts and gravitational effects. Light from the Great Wall took 10 billion years to reach us. We observe it as it was when the universe was only 3 billion years old. At that time, structure formation had less time to operate. Gravity had fewer years to amplify density fluctuations. This makes the structure's size even more puzzling. It formed too early to reach such scales under standard models. Some cosmologists remain skeptical about the Great Wall's reality. They argue that statistical analysis used to identify it might be flawed. Clustering could be random coincidence rather than physical connection. More data is needed to definitively confirm or refute the structure. Upcoming surveys will map more galaxies and gamma-ray bursts, clarifying whether the Great Wall truly exists as described. If confirmed, the Great Wall forces us to reconsider cosmic structure limits. Perhaps no hard limit exists. Maybe given enough space and time, arbitrarily large structures can form. This would profoundly change our understanding of cosmological evolution. It would suggest the universe organizes itself at scales beyond what we imagined possible. The Great Wall marks the edge of known structure, beyond individual objects, beyond clusters, beyond superclusters and filaments. This entity represents the largest organizational unit we have found. Whether it is the true limit or merely the current observational boundary remains unknown. The universe might harbor even larger structures waiting to be discovered, but massive as these structures are, they are solid matter compared to the vast, empty regions that separate them. Between galaxy filaments sits something unsettling. The boat's void stretches 330 million light-year across, nearly spherical, containing almost nothing. This supervoid occupies a region where roughly 3,000 galaxies should exist based on average cosmic density. Instead, we find only 60. The rest vanished or never formed, leaving a hole in the fabric of cosmic structure. The void was discovered in 1981 during a galaxy survey. Astronomers measured galaxy redshifts to map three-dimensional positions. In one region, barely any galaxies appeared. At first, researchers suspected instrumentation errors. No region of space should be that empty, but repeated observations confirmed the finding. A genuine void existed, larger than anything previously known. Standing in the center of the best void would present a disturbing sight. No matter which direction you looked, darkness would dominate. The nearest galaxy cluster would sit over 165 million light-years away. Galaxies would appear only as faint points requiring powerful telescopes to detect. The isolation would be absolute. You would occupy the emptiest known region of space. Voids form naturally in cosmic structure. As matter flows toward overdense regions, it evacuates from underdense areas. Over billions of years, slight underdensities become pronounced voids. The Bose void represents an extreme example of this process. An unusually large underdense region in the early universe expanded into the supervoid we observe today. The few galaxies within the void tend to be small and dim. They formed from whatever sparse matter remained inside. These galaxies evolved in isolation, never merging with neighbors or accreting fresh gas from filaments. They represent a different evolutionary path than galaxies in denser environments. Star formation proceeds slowly. Merges never occur. Void galaxies represent cosmic hermits, cut off from the busy regions where most galaxies cluster. Some astronomers question whether the void is truly empty. Perhaps dark matter fills it, invisible to current detection methods. If dark matter distributed differently than we assume, the void might contain significant mass despite lacking visible galaxies. This remains speculative. We measure dark matter through gravitational effects on visible objects. With few galaxies present, inferring dark matter distribution becomes difficult. The void size challenges structure formation models, similar to how the Great Wall does. Voids should not grow this large in the time available since the Big Bang. Simulations produce smaller voids on average. The BO's void sits at the extreme tail of size distribution, possible but rare. Finding it might be a statistical fluke, or it might indicate models underestimate how large voids can become. Other supervoids exist. The Eridus supervoid spans approximately 1 billion light-years across, though its boundaries remain less well-defined than betas. These structures are harder to detect than galaxy clusters. You cannot see them directly. You must map what is not there by surveying what is present and noting the absences. This makes void catalogs less complete than cluster catalogs. Cold spots in the cosmic microwave background might correlate with supervoids. When light passes through voids, it experiences a slight energy loss due to the integrated gravitational potential. This creates cold spots in the microwave background temperature map. Some observed cold spots align with known supervoids, though the correlation remains debated. Not all voids produce detectable imprints. The void's influence on nearby structure remains minimal. It does not pull galaxies inward because it contains little mass. Voids are passive features, regions gravity forgot to fill. They affect cosmic evolution by creating space where galaxies cannot form, but they exert no active influence on surrounding areas. Traveling across the Bose void at light speed would take 330 million years. Starting from one edge, you would race through nearly empty space for that entire duration. Occasional small galaxies would flash past every few million years. Otherwise, nothing would mark your passage. The void offers no landmarks, no interesting features, just emptiness on an incomprehensible scale. The void reminds us that the universe consists mostly of nothing. Matter concentrates in narrow filaments and nodes. Everything between is vacuum sprinkled with occasional isolated galaxies. We focus on where galaxies cluster because that is where activity happens. But measured by volume, voids dominate. The universe is more empty space than anything else. Yet even more mysterious than vast voids is a phenomenon suggesting something beyond our observable universe tugs on everything we can see. Galaxy clusters in one region of the sky move differently than expected. They drift in a common direction at speeds around 1/800,000 Bauer-ph independent of cosmic expansion. This motion, called dark flow, suggests something massive beyond our observable universe pulls on everything we can see. The existence of dark flow challenges the assumption that our observable region represents a typical sample of the entire cosmos. The discovery came from studying the cosmic microwave background. When light from this ancient radiation passes through galaxy clusters, it gains a tiny energy boost. This effect, called the Sunyaev-Zeldovich effect, allows astronomers to measure cluster velocities. By analyzing hundreds of clusters, researchers found a coherent motion superimposed on random velocities. The clusters moved together, flowing toward a point beyond the observable universe's edge. The flow direction points roughly toward the constellation Centaurus, but the source lies far beyond anything we can observe. Light from that region has not had time to reach us since the Big Bang. Whatever causes dark flow exists outside our cosmic horizon. We see its gravitational effects but cannot observe the object itself. This raises profound questions about what lies beyond our visible universe. Several explanations for dark flow have been proposed. One suggests massive structures beyond our horizon, perhaps enormous clusters or superclusters far larger than anything in our observable region. Their combined gravity pulls on clusters we can see. This implies our observable universe is not representative of the whole. It sits in a region biased towards certain structures. Another explanation invokes physics from before the Big Bang. If the universe existed before our cosmic epoch, structures from that earlier era might influence matter today. Density variations from pre-Big Bang times could create flows we observe as dark flow. This requires accepting that the Big Bang was not the absolute beginning, merely a transition event. Some physicists propose that dark flow indicates our universe is one bubble in a larger multiverse. Other bubble universes might exert gravitational influence across the boundary, separating them. What appears as flow toward empty space could actually be attraction toward another universe. This idea stretches physics beyond current testable limits, but remains theoretically possible. Skeptics question whether dark flow is real. The measurements are difficult and rely on subtle effects in the cosmic microwave background. Systematic errors could mimic a coherent flow. Later analyses using different data sets found weaker evidence or no significant flow. The dark flow claim remains controversial. Not all astronomers accept it as confirmed. If dark flow is real, it has profound implications. It would mean our observable universe represents only a small, possibly unrepresentative sample of a much larger cosmos. The true universe might extend far beyond our horizon, containing structures and variations we cannot see. This humbles our cosmic perspective. What we observe would be a tiny window onto something vastly larger. The flow velocity around 1/800,000 nph sounds enormous, but it represents only a small fraction of cosmic expansion velocities at large distances. Galaxies at the observable universe's edge recede at speeds approaching light speed due to expansion. Dark flow adds a relatively modest component to those velocities. Still, any coherent motion at such scales demands explanation. Upcoming cosmic microwave background missions might settle the question. Better data on the Sun v. Zeldovich effect and improved cluster catalogues will refine flow measurements. If dark flow disappears with better data, it was likely a statistical fluctuation or systematic error. If it persists, we must take it seriously. Dark flow represents one of those tantalizing hints that our understanding remains incomplete. It sits at the edge of detectability, difficult to confirm or refute with current data, like dark matter and dark energy before it. Dark flow might eventually be accepted as real and force us to revise cosmological models, or it might fade away as a measurement artifact, leaving standard models intact. Either outcome teaches us something. If real, we learn the universe extends far beyond our vision. If false, we learn the dangers of over-interpreting marginal signals. Science progresses through such controversies, gradually clarifying what is real from what is not. The cosmic microwave background itself, which hints at dark flow, preserves the oldest light in the universe. Everywhere you look in the sky, ancient light surrounds you. The cosmic microwave background fills space uniformly, coming from all directions at once. This radiation represents the oldest light in the universe, released roughly 380,000 years after the Big Bang. That light has traveled through space for over 13 billion years, cooling from thousands of degrees to just under 3 degrees above absolute zero today. Before the cosmic microwave background formed, the universe was opaque. Free electrons scattered photons constantly. Light could not travel far before colliding with matter. The universe resembled the inside of a star, hot and dense, with radiation trapped by constant scattering. Then the universe cooled enough for electrons to combine with protons, forming neutral hydrogen. With free electrons gone, photons could travel unimpeded. The universe became transparent. Those first free photons are what we detect as the cosmic microwave background. The radiation appears remarkably uniform. Temperature varies by only 1 part in 100,000 across the sky. This uniformity posed a problem for cosmology. Regions separated by vast distances show nearly identical temperatures. How did they equilibrate when light had insufficient time to travel between them since the Big Bang? This is called the horizon problem. Inflation theory solves the horizon problem. It proposes that the universe expanded exponentially fast for a brief moment immediately after the Big Bang. Regions now separated by billions of light years were in contact before inflation. They equilibrated to the same temperature. Then inflation stretched them far apart. This explains the microwave background's uniformity while preserving the Big Bang model. Tiny temperature fluctuations in the microwave background seed all cosmic structure. Slightly warmer regions indicate higher density. Gravity amplified these density contrasts over billions of years. The fluctuations grew into galaxies, clusters, and the cosmic web. Everything we see today traces back to quantum fluctuations in the infant universe preserved in the microwave background pattern. Detecting the cosmic microwave background required sensitive instruments. Early measurements used radio antennas designed for satellite communications. Arno Penzias and Robert Wilson accidentally discovered it in 1964 while testing an antenna for Bell Labs. They detected persistent noise coming from all directions. After eliminating all possible sources, including pigeon droppings in the antenna, they realized they had found the echo of the Big Bang. Later, satellites mapped the cosmic microwave background in exquisite detail. COVE, WMAP, and Planck each produced progressively better maps. These missions measured temperature variations to millionth of a degree. The maps revealed the structure of density fluctuations in the early universe. From those patterns, cosmologists extracted parameters defining the universe's composition, age, and geometry. The cosmic microwave background confirms the universe is flat geometrically. Parallel lines remain parallel at cosmic scales. This flatness sits finely balanced. Slight deviations would cause the universe to curve into a sphere or saddle shape. The observed flatness supports inflation theory, which predicts exactly this geometry. Polarization in the cosmic microwave background provides additional information. Light waves oscillate in specific directions. By measuring polarization patterns, astronomers can test theories about the universe's earliest moments. They search for imprints of gravitational waves from inflation. These primordial waves would leave a distinct polarization signature. So far, no confirmed detection exists, but searches continue. The microwave background cools as the universe expands. Its temperature has dropped from thousands of degrees to 2.7 degrees Kelvin today. Eventually, billions of years from now, it will cool further, becoming harder to detect. The radiation will redshift into longer wavelengths, fading into the background noise of an ever colder cosmos. Observing the cosmic microwave background provides a snapshot of the universe 380,000 years after the Big Bang. We cannot see earlier times directly. Before then, the universe was opaque. The microwave background represents our earliest possible view. It is a baby picture of the cosmos, showing its structure before galaxies, stars, or any familiar objects existed. Maps of the cosmic microwave background hang in cosmology departments worldwide. These images show the universe in its simplest state. Tiny red and blue splotches indicate warmer and cooler regions. From those splotches, everything we know emerged. The maps provide evidence for the Big Bang, confirm inflation, measure cosmic parameters, and validate our understanding of structure formation. Few scientific images carry more weight, but the cosmic microwave background reveals only ordinary matter's history. Most of the universe consists of something completely different. Galaxies rotate too fast. Stars in the outer regions of spiral galaxies move at speeds that should fling them into intergalactic space. Visible matter provides insufficient gravity to hold them in orbit, yet they remain bound, circling the galactic center for billions of years. Something unseen adds mass, creating extra gravity. We call that something dark matter. Dark matter outweighs all visible matter by roughly 5 to 1. For every star, planet, gas cloud, and dust particle, we can see 5 times more mass exists in invisible form. This dark matter does not emit, absorb, or reflect light. It interacts through gravity alone. We detect it only by measuring how visible matter moves under its gravitational influence. Evidence for dark matter comes from multiple independent observations. Galaxy rotation curves provide the clearest example. Measuring how fast stars orbit at different distances from the galactic center reveals the mass distribution. The curves stay flat far from the center, indicating significant mass in the outer regions. But those regions contain few visible stars. Dark matter fills the gap. Gravitational lensing offers another confirmation. Massive objects bend light passing nearby. Galaxy clusters bend light from background galaxies, creating distorted arcs and multiple images. By analyzing the distortion, astronomers calculate the cluster's total mass. The result far exceeds visible matter. Dark matter dominates the cluster's mass budget. The cosmic microwave background's temperature fluctuations depend on dark matter. Normal matter alone cannot produce the observed pattern. Adding dark matter in the right proportion matches observations perfectly. The microwave background independently confirms dark matter's existence and measures its abundance. What dark matter consists of remains unknown. It cannot be ordinary atoms. We have accounted for all the protons, neutrons, and electrons in the universe. Not enough exists to provide the required mass. Dark matter must be something else. Likely a new particle predicted by physics beyond the standard model. Several candidates have been proposed. WIMPs, weakly interacting massive particles, were long favored. These hypothetical particles would interact through gravity and the weak nuclear force, but not electromagnetism. This would make them invisible and difficult to detect. Experiments deep underground search for WIMPs colliding with ordinary matter. So far, no confirmed detections exist. AXI represent another candidate. These extremely light particles would form a diffuse cloud around galaxies. Their quantum properties would create interesting effects at large scales. Experiments search for axions by looking for their interaction with strong magnetic fields. Again, no confirmations yet. Primordial black holes offer a non-particle explanation. If many small black holes formed in the early universe, they could provide dark matter's mass without requiring new particle physics. However, observations constrain this possibility. Too many primordial black holes would create detectable effects we do not observe. They can account for only a small fraction of dark matter at most. Dark matter-shaped cosmic structure. In the early universe, dark matter clumped first. Its gravitational wells attracted normal matter. Gas flowed into dark matter halos where it eventually formed galaxies. Without dark matter, structure formation would have proceeded much more slowly. Galaxies might not have had time to form at all before cosmic expansion diluted matter too much. Dark matter halos extend far beyond visible galaxies. The Milky Way's dark matter halo likely reaches hundreds of thousands of light years from the galactic center. This halo contains most of the galaxy's mass. Visible stars and gas occupy only the inner region. We live embedded in a dark matter sphere that dominates our gravitational environment. Detecting individual dark matter particles would revolutionize physics. It would confirm the existence of matter beyond the standard model. It would open new research directions into particle interactions. Experiments worldwide pursue this goal using increasingly sensitive detectors. Each null result narrows the possible parameter space for dark matter properties. Some physicists question whether dark matter exists at all. They propose modifying gravity instead. Perhaps Einstein's equations break down at galactic scales, producing effects we misinterpret as dark matter. These modified gravity theories face challenges explaining all observations consistently. Dark matter remains the simpler explanation, requiring fewer assumptions and matching more data. Dark matter's dominance humbles us. Most of the universe's mass consists of something we cannot see, touch, or directly detect. We have built our understanding of physics around particles we can observe in laboratories. Dark matter operates beyond that realm. It reminds us how much remains unknown. Yet, dark matter represents only part of the cosmic budget. Something even more mysterious dominates the universe's energy content. The universe is not just expanding, it is accelerating. Galaxies recede from each other at ever-increasing speeds. This acceleration defies intuition. Gravity should slow the expansion, pulling matter back together. Instead, something pushes outward, overpowering gravity's attraction. We call that something dark energy. Dark energy makes up roughly 68% of the universe's energy budget. Dark matter accounts for 27%. Normal matter, everything we can see and touch, constitutes only 5%. The universe consists primarily of two things we do not understand. With familiar matter as a small minority component, discovering cosmic acceleration shocked astronomers. In the late 1990s, two teams studied distant supernova to measure the universe's expansion history. They expected to find expansion slowing over time. Instead, distant supernovae appeared dimmer than predicted. This indicated they were farther away than expected. The expansion had accelerated, carrying them to greater distances than a steadily expanding universe would allow. The discovery won the Nobel Prize in Physics in 2011. It forced cosmologists to revise their models fundamentally. Something previously unaccounted for was driving expansion. The simplest explanation invoked Einstein's cosmological constant, a term he introduced in his equations, then later abandoned. The cosmological constant represents energy inherent in empty space itself. Vacuum energy sounds paradoxical. How can empty space contain energy? Quantum field theory predicts it. Virtual particles constantly pop into existence and annihilate in vacuum. This quantum activity contributes a baseline energy density. If that energy density is positive and non-zero, it exerts negative pressure, pushing space apart. This matches dark energy's observed effects. But quantum field theory predicts vacuum energy vastly larger than observed. The calculated value exceeds measurements by 120 orders of magnitude. This is called the cosmological constant problem. It represents one of the worst prediction failures in physics. Something cancels almost all the vacuum energy, leaving only a tiny residue to drive cosmic acceleration. We have no good explanation for this fine-tuning. Alternative theories propose that dark energy is not constant. Perhaps it changes over time. Quintessence, a hypothetical scalar field, could slowly evolve, changing the universe's expansion rate. This differs from a true cosmological constant. Current observations cannot distinguish between constant and evolving dark energy. More precise measurements of distant supernovae and cosmic expansion might resolve the question. Dark energy operates only at the largest scales. Within galaxies or even galaxy clusters, gravity dominates. Dark energy's influence is too weak to overcome local gravitational binding, but across hundreds of millions of light years, dark energy wins. It drives superclusters apart, ensuring they can never merge, despite gravitational attraction. The future of the universe depends on dark energy. If it remains constant, expansion will accelerate forever. Galaxies will recede from each other at ever faster rates. Eventually, distant galaxies will move away faster than light can travel. Their light will never reach us. The observable universe will shrink as more galaxies disappear beyond our cosmic horizon. Trillions of years from now, the night sky will darken. Only galaxies in the local group, bound by gravity into one merged system, will remain visible. Everything else will have receded beyond detection. Civilizations arising in that distant future might never discover the wider universe. They would see only their local galaxy against absolute darkness. If dark energy strengthens over time, the outcome becomes more extreme. A big rip might occur. Acceleration would eventually become so strong that it tears apart gravitationally bound structures. First, galaxy clusters would dissolve. then individual galaxies. Eventually, stars, planets, and finally, atoms themselves would be ripped apart by runaway expansion. The universe would end in total disintegration. Alternatively, dark energy might weaken or reverse. This could slow expansion and perhaps trigger a big crunch. The universe would collapse back on itself, density and temperature rising until everything merges in a final singularity. This scenario appears less likely based on current data, but it cannot be ruled out completely. Understanding dark energy requires better measurements. Upcoming surveys will observe millions of galaxies and thousands of supernovae. They will map the expansion history in unprecedented detail. Any deviations from constant dark energy should become apparent. These observations will constrain theories and possibly rule out entire categories of explanations. Dark energy represents the universe's greatest mystery. It dominates cosmic dynamics, yet remains completely unexplained. We measure its effects precisely, but understand its nature not at all. Solving the dark energy problem might require new physics as revolutionary as relativity or quantum mechanics, or it might demand rethinking fundamental assumptions about space and time themselves. The accelerating expansion sets limits on what we can ever observe or reach. Light has traveled for 13.8 billion years since the Big Bang. You might expect the observable universe's radius to equal that distance. It does not. The edge of what we can see lies 46 billion light-years away. This apparent contradiction arises from cosmic expansion. While light traveled toward us, space itself expanded, stretching the distance between its starting point and Earth. Imagine a photon leaving a distant galaxy 1 billion years after the Big Bang. It travels toward us at light speed, but during its journey, space expands. The galaxy the photon left continues receding. By the time the photon reaches Earth, the galaxy sits much farther away than one would calculate from light travel time alone. The expansion stretched the separation. The observable universe contains roughly 2 trillion galaxies. Each galaxy holds billions to trillions of stars. The total number of stars exceeds human comprehension. Estimates suggest around 1 septillion stars exist within our cosmic horizon. That number is 1 followed by 24 zeros. More stars than grains of sand on all Earth's beaches. But the observable universe represents only what light has had time to reach us. The entire universe likely extends far beyond. If the universe is infinite, then infinite galaxies and stars exist beyond our view. We can never observe them. Light from those regions has not had time to arrive. Expansion might be carrying them away faster than light can cover the growing distance. The cosmic horizon represents a fundamental limit. We can never see beyond it with any technology. Light from beyond the horizon can never reach us. As the universe ages, more distant regions will cross our horizon as their light finally arrives. But cosmic acceleration works against this. Dark energy accelerates expansion. Distant galaxies recede faster over time. Eventually, regions crossing inside our horizon will be offset by regions accelerating beyond it. The horizon creates an observational bubble around us. Every observer in the universe occupies the center of their own bubble. The bubbles overlap partially. Observers in Andromeda see some galaxies we cannot see, and vice versa. But their horizon extends the same distance in all directions from their location. The universe has no special center. Every point is equivalent. Beyond our horizon, the universe might look completely different. Our region might have properties not shared elsewhere. The laws of physics should remain constant, but local conditions could vary. Density, expansion rate, and structure might differ in regions we can never observe. We sample only a finite volume of potentially infinite space. Some models propose the universe is finite but unbounded. It wraps back on itself like the surface of a sphere. If you traveled far enough in one direction, you would eventually return from the opposite direction. In such a universe, the total volume is finite. Light could in principle circle the entire space. We might even see distant images of our own galaxy from eras long past. Current observations do not support this topology, suggesting the universe is either infinite or much larger than our observable region. The observable universe expands over time. More distant regions come into view as their light reaches us. But this growth slows and might eventually reverse due to dark energy. The accelerating expansion means some galaxies currently visible will eventually recede beyond our horizon. Their light will redshift into invisibility. The observable universe might shrink in the far future. Calculating the observable universe's size requires general relativity and detailed cosmological models. The expansion rate changes over time. Early inflation expanded space rapidly. Later, matter dominated and expansion slowed. Recently, dark energy took over and expansion accelerated again. Integrating these different epochs yields the 46 billion light-year radius. This radius represents a moving distance. It accounts for expansion over cosmic history. The distance to the most distant observable galaxies measured along the current fabric of space equals 46 billion light-year. But those galaxies appear as they were over 13 billion years ago. We see their past, not their present. Their current state lies beyond our knowledge. The observable universe's edge is not a physical barrier. Space does not end there. No wall or boundary exists. It simply marks how far light has traveled since the Big Bang. Beyond it, the universe presumably continues. Whether it extends infinitely or curves back on itself at some larger scale, we cannot say. Our observations are limited to this 46 billion light-year sphere centered on Earth. Understanding that our view is finite and bounded humbles cosmic perspective. We see only a small, possibly unrepresentative sample of reality. The true universe might be vastly larger, containing structures and variations we can never detect. Our theories and models apply only to what we observe. Beyond that, speculation replaces knowledge. But what might exist beyond our view raises mind-bending possibilities.